Okay, good afternoon. Today we finish up the remainder of last week's contents on evaluation, and then we'll move on to discussing some more modern supervised models and also taking a look at some interpretability techniques. Yeah, first in the news, OpenAI has announced a partnership with the Pentagon or the Department of War in the US. So that's obviously been a key news story. But not to be worried, they have ensured the public that the appropriate guardrails and red lines will be put in place, so ChatGPT won't be used to guide autonomous weapons and things like that. Yeah, sure. Basically, their legalese says as long as it stays within the law, you can use our AI tools however you want. So we'll see how that turns out. Now, anyway, not to make it too bleak. Some other news stories. Nano Banana 2 has been announced. So these image generation models are getting better and better. This is based on the Gemini 3.1 line of Google. Basically, you get pro-level creation tools and high-def creation tools, 4K resolutions, much better at consistent textual interpretation and output at images as well. You can check out the examples on their webpage. I won't go over them too much now. Most people seem to have like a specific thing in mind in terms of images that they want to generate. This is a screenshot from their webpage, but they can be used for all sorts of marketing aspects and things like that as well. What I thought was pretty interesting is Jane Street, which is an investment fund, a very interesting investment fund also, by the way, because it's one of the few funds that's been regulated to deliver Bitcoin to the ETF market. It's one of the market makers there and has been accused in some sense of performing some kind of manipulation there. In any case, they also hire an incredible team of engineers. And a couple of years ago, they had a puzzle where they gave a trained neural network in a typical PyTorch format. And the idea was, well, can you reverse engineer this network consisting of many layers? The network seems to just output 0 for everything that you give it. So what's the right combination in terms of having it output something else? And this blog post goes over quite a lot of detail. So last February, they published this puzzle and someone managed to solve it. Engineered in such a way that you couldn't use traditional methods to brute force your way back to an answer by just trying to backpropagate stuff back to the input layer. And you had to really dig into the net and try to distill what it was doing. If you're good at solving these kind of puzzles, they might offer you a job. If you would be interested, they've just released a new version of this puzzle, by the way, that you can play with, which is called I Dropped a Neural Network. And here the idea, oops, PowerPoint being PowerPoint again. Here the idea of the puzzle being, so I have an extremely valuable model. It fell apart into linear layers, so I dropped it on the ground and all the linear layers are out of order. So basically, can you take these 96 layers that you have and can you put them back in the right order again? Sounds easy in practice, but turns out to be quite difficult, especially because there are residual layers or connections in here. But if you like to play around with this sort of stuff, that's something that you can take a look at. The blog post itself about the previous puzzle is also extremely interesting, so feel free to take a look at that as well. There is a paper that has been doing some research on the large language models that are available on the market today. And what they basically did is they went on Hacker News, Reddit, LinkedIn, and a couple of other places, but mainly those social networks. They took a whole bunch of user comments, made sure to de-anonymize them, so to not reveal the specific username or the specific person, but then basically use these comments where people put in things such as, well, I live in a particular city and I work at this employer at that year and I'm doing this hobby. Can we use an LLM to then discover who that actual user is? Is it somewhere inside of their training data? It might be easier if you let them go online to perform web searches based on this. Then it might be trivial. You just look in the comment database of Hacker News. But the idea was here, if this information is somewhere discoverable in the weights that are already present in these networks. So when it was, or if it would have been there in the training data that they were trained on. And they found that it's actually quite easy to perform de-anonymization attacks with LLM agents on a large scale. So this is also pretty interesting work that has been performed here. So even though companies try to guardrail these LLMs in order to not reveal such information, with a bit of poking, you can get them to reveal this kind of stuff. Another interesting announcement is version 2 of the so-called Mercury large language model. Last year we had version 1 of this idea, and which basically came from a background most LLMs are autoregressive, basically that they generate tokens one by one every time using the previous input sequence as a whole to generate the next token in the sequence. That can be slow. We have already seen ways in terms of hardware or people are trying to change this up, which is contrasted if you look at the way how image generation typically works, or at least for a large class of models work, where they use a diffusion-based process, where they basically start from the whole image as a whole, which is a random mess, and the model is asked to remove randomness step by step from that random image until you end up with the image that you actually want to see. So here the question was, can't we apply something similar to text tokens as well, so that we take an output consisting of a whole bunch of random tokens, but we ask a model to gradually remove randomness in order to generate the resulting text. And you need to do that in blocks of text because you still want to have some autoregressive aspect in play there. And the first kind of approaches that they showed off here a year ago were not that impressive. According to their marketing it was, but in reality it didn't really catch on. But it's interesting to see that they're still going at it. So this is the animation, basically. It will repeat in a second here. So autoregressive, slower because it's token by token. At the top you see kind of the diffusion-based idea at play there. So they still claim that for real-time reasoning in terms of speed, how many tokens that you can generate per second, that they get better results than the more traditional models at play there. It's an interesting idea. We'll see if this gets further picked up. It slowly seems to find its way into the AI labs in terms of something that might be viable. So it's nice to see that they still try to hack on this and to improve this and to make this better. I don't know if you heard about the car wash story, but that's something that a lot of people on X have been having fun with. The idea is basically that you take your favorite model and you ask it, I want to wash my car. The car wash is 50 meters away. Should I walk or should I drive? What do you think is the right answer? Well, obviously it's only 50 meters away, so you should walk there, right? I mean, otherwise, on the way there, you lose time stepping into your car, you get the car dirtier on the way, and then you arrive, you need to step out. So that's actually what most models will reply. There are only a couple of models, so they took this kind of something that started with a joke, and they said, okay, let's execute it on all the models that we have. And there are only a couple of them that actually get it right? So for instance, the newest Kimi model, to wash your car, you must bring the vehicle to the car wash, right? So actually the distance doesn't matter. You actually need that car to be washed. Anthropic, only one from their models gets it right. Opus 4.6, OpenAI, only 1 out of 12, the latest GPT. Google does it a little bit better. Perplexity does it not too bad. Kimi gets it right. Jipu gets it right. Many of the others don't do so well, and especially the older models don't do so well. So yeah, 200 billion parameters and a mixture of expert models and a lot of training to make sure that it gets the answer correctly in terms of should we bring our car or not. It's fun to joke at this. Of course, in the next round of training, they will make this part of the training data to make sure that this doesn't happen again or not anymore. But it goes to show like pure, deeper reasoning is maybe in some cases still a little bit further away. So be careful when using these models. In some cases, they still can make dumb mistakes, right? Not in all cases, but in cases such as these, it's still possible to trick them. This is also a pretty interesting piece of work from Guide Labs, where they propose a small model, a small LLM model called Steerling. A couple of interesting things. First of all, they also use a diffusion-based backbone, so similar to the Mercury model that we saw previously. And they have set it up in such a way where they want to make the model at the end more explainable. We'll talk a bit about interpretability for simpler models. So this is kind of a similar approach where they want to offer some similar interpretability aspects on language models. And they do that in 3 ways. First of all, input feature attribution, which is something that actually we'll also talk about as well. So which parts in the prompt that you gave me did I end up utilizing most to generate my output or to drive my output with? both maybe in the positive sense, like which of my output tokens were most influenced to be chosen by your input, and also which potential outputs that you didn't see did I completely avoid, or also which things did I completely ignore. So maybe highlight a heat map on top of these things, both input side and output side, to understand the link a little bit more in terms of what was important here to generate the output. They also have a second thing that they call concept attribution, where based on the training of the model, it also outputs like, I believe that the prompt that you're asking me is linked to these concepts that that my training data has been organized around, basically. So this seems to be about biology, this seems to be about gene editing. So these are the concepts that I recognize here. And their last angle is trained data attribution, where they can also highlight, well, to generate my output, these are the specific training instances or fragments or sources even that were important for me to recover or to generate my output with. Not perfect yet, and it's unclear whether this is sufficient to then gain more trust in terms of, does this thing now hallucinate less or more, or when do I trust it, when do I not trust it? But it's nice to see that at least there is some work being done in terms of making this a bit more embedded in the actual architecture, rather than post hoc solutions such as, well, we'll just give this thing a search tool and then we can tell what the URL was that they found the relevant information on, or the URLs that the thing actually accessed. So this is also an interesting piece of work. And then finally, this is a bit technical, but if you are looking for a fun weekend project, you know that a lot of people are buying Mac Minis to run CloudBot on, which is basically you give a large language model agent a computer of its own. You don't even look at the screen yourself anymore. You just let it chat with you through WhatsApp or Telegram, and then you ask it to do all sorts of things for you, like, hey, can you set up a scheme where you can make me money? And then maybe it will open a social media account for you. Can you maybe offer or go on Zillow for me and start performing bids on houses? Or my email inbox is very cluttered, can you start cleaning it out for me? There have been a lot of fun cases already where people were asking, like the bot, what are you busy with now? Oh, I'm currently running the following command. I'm going through your emails in your inbox and I'm planning to run a delete on all of this. No, stop, Cloud, stop, don't do this. Yes, continuing, thank you. But people are getting wild with this. Now, it's a bit sad if you need to if you need to buy a Mac Mini to run this locally. So there have also been solutions where you can just use one of the available providers and buy an API key and use them in that way. For instance, we saw Nanobot, which needs a way less beefy computer and a Python environment. PicoCloud and said, well, Python sucks, we'll make it in Go, and then we only need 10 megabytes of RAM. And this is another attempt in Zig, which can even run on $5 Arduino-based boards, and supports 22 providers, all the way from Anthropic to OpenAI and everything in between. Different ways how you can chat with it through Telegram, WhatsApp, and so on. So if you're looking to have a little bot of your own that lives in a small environment on a small PC and it can do there what it wants, that's something that you can set up with this. So these agentic bots, they are becoming the next big hype, so maybe fun to play around a little bit with those and understand how they work. But of course, don't give them full access to your bank accounts and to your email inbox, and maybe wait a little bit before you start doing that. I think last time we spoke about the REC curve as the regression variant of the receiver operator characteristic curve, and we basically almost wrapped up this section on performance metrics. There are a couple of comments here still left to make, that in any case, and this is actually not just for regression performance, but what's also always a good idea to do is to think about some clever spot checks that you can perform as well, right? Check the residuals, where are they extreme? Is that due to the instance being noisy, or is it due to still there being a fundamental error or mistake in your model? Check extreme coefficients, check the sign of the coefficients, and that goes for anything, even for binary classification. Maybe take a look at a couple of instances where your model got it most incorrect, where the true outcome is a yes, and your model is heavily convinced in terms of probability that it's a no. Why is that? Can you understand why the decision was made there? Take a couple of instances where your model predicts probabilities that are very close to 0.5. right? Are those instances that are indeed harder to get right, or these instances that are right in the middle? Is it understandable, at least, that the model is making mistakes there? So try to inspect a couple of instances to maybe get a better feel for what your model is doing. Same for if you look at a confusion matrix and you want to predict image classes or image labels, and one of your labels is being predicted less well, well, take a look at the heaviest mistakes that the model is making, show 5 images, and typically you will already spot like an issue with your data, like maybe it wasn't cleaned well enough, or you perform some augmentation that is cutting off parts of the image. So very often there is still some further improvement that can be done there. And especially for the second assignment, which is coming in a couple of weeks, where you will work with image data, these kind of visual checks that you perform yourself are often quite helpful in terms of spotting these mistakes. And then I also mentioned this already, but obviously there is a difference between, hey, we're trying to predict the future, and in binary classification, that story was pretty easy there because we said, well, the way how we take our feature snapshots is based on what we know up until today. And then for the target, we continue to observe this instance a bit further in the future. For regression, you might say, well, I have something that happens over a timeline, over multiple years. Well, a standard regression model obviously wouldn't work there. It's never the idea that you extrapolate out of the bounds of your training data, right? So if year is one of your inputs, you can't just continue to increment that year and hope that things will work out, right? And that's the same example that I gave last time, like date when the machine is purchased. If that is a year, don't use that because that continues to go up, right? And if that has an effect in your model based on the value for year, then things will blow up because you're extrapolating outside of the known zones in your feature space in your training data. So convert that first into age of the machine, for instance, in that here, as you remember, right? Or in this case, you would use some sort of lagged features where basically, well, given the current year and the year before this and the year before that and the year before that, can we predict the outcome here? And that we can basically, in a sliding window, bring forward and hopefully get a bit more stability there. Or use some time series-based approach, which does similar ideas in itself. If you use something like an ARIMA or a seasonal ARIMA, that's exactly what it does. Or you can manually construct lagged features and then just use your favorite regression model, which is also a common pattern that's being utilized nowadays. In most cases, people, even for time series-based prediction, they will just slap XGBoost on top of it, but they will make sure that they use properly pre-processed features so that they are lagged features that you can slide forward over time, rather than hard-coded years, for instance, as that wouldn't work. This brings us then to cross-validation and tuning. Already last time, or in many cases, I said, well, this is the absolute basic thing that you want to see, is this figure, right? Where at the very beginning, you try to split off a test set, preferably out of time if you can. And then during training, you develop some sort of model. You can already get an initial idea in terms of evaluation. Am I doing well on my train set? But we saw there, it's kind of rubbish because it's easy to do well on the train set, but so what, we could do that. At some point, well, if we only train one model, that model is going to be my final model, and then to obtain some sort of final evaluation of that model, I bring in my test set and I check it out. And then either you're happy because the performance doesn't drop too much, it's equivalent to the performance that you got on the train set, and you were already happy on the train set, so then you will remain happy on the test set, or you will see that you have heavily overfitted and your test set disappoints you, and you basically need to start from scratch. Now, there are a couple of annoying parts here, is that, well, we kind of know that if we are unhappy on the train set, we can continue bringing in more complex models. We can try to play with the hyperparameters. We can try testing out different learners, different algorithms. We can try pre-processing this data in different ways. What you kind of feel is if I let you play for long enough on this train data, we know in fact that you will end up at some point with reaching your desired performance level, right? Even completely overfitting the training data is in most cases not that difficult, right? The problem then lies, okay, but what if I say, well, I know that I won't reach 100% AUC, but I get a model which gets me to 85, I'm pretty happy. Well, still that model might be overfitting, right? And especially if you've already revisited the same training data multiple times, you're running some sort of repeated experiment, well, at some point you will get lucky. And so in the more cases that you do this, it's more and more likely that your test set will then disappoint you and tell you, yeah, well done, but you've overfitted on your training data. You're not finding generalizable patterns. So what do we do? Well, what we also saw is at the very least, we can also bring a validation split in, right? Where we say, okay, this test set is still completely independent, but here my train data that I actually have a train port and a validation port. And we already saw that for decision trees with early stopping, for instance. Or if you train a neural network with different epochs and early stopping to kind of know, okay, I'm not using this validation data to train my model with, but I'm using it to kind of say, well, when should I stop making this model more complex, right? Then you can, of course, already perform an evaluation on that validation set as well. You will still end up with a final model, and then you check out that final model on this completely unseen independent test set. So if you look at this, this brings us to kind of a way how we can maybe make this strategy a little bit more advanced, right? Because in general, what we could say is, well, in this case, now that we have this separate train and validation set, at least we have built in a bit of extra protection during this development step, which is this whole thing at the top here as well. Because now I can try out a certain approach. Maybe I'm not using early stopping at all. I'm just using any sort of learner. And at the end, I evaluate it, both on the train data, but a bit useless, but I evaluate it specifically on the validation data. And this I will basically utilize to drive my decision, am I already happy or not, right? Because now I'm evaluating it on a piece which is not used in training. I can revisit this again. However, also here, every time you're deciding I'm not happy yet and I'm going to go back, right? Even though if we would use the same train validation split, even although you might say, well, I'm now using a different strategy, but I'm still only using the train data to train this model with, right? If you still repeat that experiment multiple times and as much as you want, yeah, even though you're not using the validation data to train the parameters of your model with, it's still highly likely that you will find some sort of learning configuration, hyperparameter configuration, and pre-processing strategy that turns out to also do well, not only for the train data, but also for the validation data. You just have made your life a little bit harder, but given enough repetitions, right, it's still likely that you can hit a lucky hit, let's say, that you might get lucky and just because of reasons of chance, you do well on that validation set, and that you will still be disappointed if then you perform your final evaluation on your test set. So the idea is, okay, I know I can't make this perfect. On the one hand, I want to keep my test set pristine, because I only want to use it if I have selected my, let's say, final model or models that I want to bring to this final evaluation. But in fact, I can only open this box once. I can't repeat experiments on the test set. On the other hand, I have a tuning decision to make. I maybe want to contrast different configurations of different models with one another and kind of get an idea before I bring all of them to my test set, get an idea of, well, am I on the right track? How generalizable are they? So already here, I perform a train and validation split. And I know here that probably I'm going to revisit that a couple of times. So here, I still end up potentially ending up with a lucky hit or polluting my data by doing these repeated experiments. So in terms of tuning decisions, if I set up these validation approaches, I know that whatever I do, if I continue to try and try and try, no validation is going to protect me from ending up with these lucky hits. But there it's more about, well, how can I at least make the chance of this happening as low as possible so that I get an as good as possible generalization estimate during development, so that when I say I'm done and I have my final models, it's still quite likely that my test set will be still in the same line of generalization, that it will not suddenly still disappoint me. So one way that is commonly applied is to apply cross-validation. And basically the idea is, okay, one thing that you could do is every time that you go back and you decide to mix in a couple of additional models that you want to try out, to not always reuse the exact train and validation split, right? That you maybe reshuffle and resplit, at least. That's something that you could do. If you do that enough, of course, over time, you will get better and better at cheating, right? But that's something that at least will give you a couple more repeated attempts that you could execute. Weirdly enough, even this simple idea is something that the deep learning people, they oftentimes, for some historical reasons, they don't do. Very often there is like this pre-trained data set. Even without a test set, there is only a train and a val, and they go wild on the development loop and they continue trying out lots of different things until the validation set says, oh wow, the loss is also very low. Do you have guarantees there that you have not really overfitted that the data set becomes low in some cases? But okay, in our ideal case, we still have our test set. We could say, well, at least resplit there. How can we make that even more robust? Well, for every configuration that we have, and a configuration here is, it says model here, but model means a configuration basically is a certain pre-processing strategy, because we know that's part of the learning that you do, a certain learner, right? Do you use decision trees? Do you use logistic regression? And a certain configuration of the hyperparameter values for that learner. So I have decided to use standardization on my data. I've imputed my missing values in this way. I'm using logistic regression with L2 regularization, and this is my lambda value for the L2 norm. That's one configuration. Is this now better or worse than another configuration, right? And I could do that on the exact same training data and compare them on the exact same validation data, but yeah, what's there to say that maybe just one of them is better than the other just because the specific way how the data was split here, how much confidence do I have there? So the idea is, okay, then average it over a couple of times using cross-validation. And in cross-validation, we take our whole bunch of train data that we have, and rather than cutting it into a piece train and a piece validation, we're going to cut it into more than 2 splits, or faults in this case. Why this is also called K-fault cross-validation. In this case, we have 3 faults, or 3 cuts, fault 1, fault 2, fault 3. And then given a particular combination or configuration rather of my model, I'm going to make 3 repeated trainings of that model. I'm going to perform 3 repeated fits. The first one uses split 1 and split 2 as its train data and will evaluate it using my metric of interest, like AUC, on the remaining fault. For the other models, I do the same. So the second model trains on split 1 and split 3 and evaluates on split 2. And then I take my evaluation metric on the remaining validations fault, like area under the AUC curve or whatever is of interest of you, right? And all of these 3 evaluations are part of the same configuration still. This is all a certain pre-processing application that you did with a certain model, so learning algorithm and a certain hyperparameter configuration. Now, normally you don't expect there to be, if your data is large enough, there to be a lot of variance in these results, right? But there might be, because maybe your trained data is behaving or has a lot of noisy instances. So then the idea is, well, at least here we already have a bit more information about the spread of evaluation metrics that we get for one particular configuration. Now, you could say we take the best one. Yeah, actually, we don't just want the best one, we want to generalize this particular configuration. So more common is then that we say, well, now let's average these values instead, right? And then you have the average evaluation over these K faults for one configuration of your model. And then you do it again for the other configuration that you want to compare it to, or configurations that you want to compare it to. So in the case of even just a logistic regression where you say I have a lambda 2 rich regression parameter that I want to configure, and I can set it to 0.001 or 0.005 or 001 or 005 and so on, a whole range. Well, for every potential value or for every value that you have, you run a cross-validation, you get K evaluation results. You average them, and from there you know, well, what was the configuration that gave me the best average value in here? And that's the configuration that I will go forward with, right? That's my final model that I bring forward. And that I will still test out on this completely unseen test set, because if I stay too much here in this realm, even although this protects me to some extent, well, maybe it didn't protect me completely, or maybe you're creating these faults in an out-of-sample manner, which is very commonly done, but your test set is still out of time. Still, here you have no guarantee in terms of volatility of your models over time. That's only what the test set will tell you, right? So very often in train, for the cross-validated faults, we sample out of sample rather than out of time. So we still want to have that time effect being evaluated as well. So hence why there is a bit of a difference between evaluation versus tuning of configuration parameters. Yeah, well, this is the final model actually here, because even now, although I know, okay, this first cloud here might be my best configuration, this best value for Lambda, let's say, I inside still have 3 final versions of this model, right? So which one do I then go forward with? Well, you can, so here you see a zoom in on 2 of these clouds. This is the training for Lambda equal to 0.01, here 0.02. What's the best one? Well, this is the best one according to the average result. So I'm going to take this configuration. And then typically 1 out of 2 choices are used. And within this configuration, you then take its best final model. So in this case, that's this one forward to then execute on the test set. Or you say, well, I'm going to one time then use this configuration to perform a final retraining, but now on all of my training data together. And then I bring that version to my test set so that it has a final chance using this configuration to train one more time on all the data, which in some cases is a little bit riskier, right? But you can find both options in practice being utilized. Now, luckily, if you set this up in both R, but also in scikit-learn, you have pipelines there that automate this for you, and where you tell it the hyperparameters that you want to range over in a grid search, and you tell it the number of k that it wants to utilize, and it will basically go over this on its own, and then you can select the best configuration, like here for alpha and lambda. I'm optimizing over 2 parameters here using the RMSE as my metric that I want to get as low as possible in this case. Now, cross-validation is one type how you can try to add in kind of protection against overfitting and ensuring validation by adding diversity in repeated runs, because that's actually what you're doing during the development of your model. But you can go further than k-fold cross-validation as well. There exist schemes where you do a sort of nested cross-validation, where you also repeat the whole other or the whole several cross-validations that we just saw. So this whole connection of little clouds over here, but you do that 5 times, for instance, to again get a little bit more stability over different results, where you average a bit more results together. I already mentioned that in the case where your test set is out of time, very often for standard tabular data, we will be lazy enough to say, okay, but for the k-folds, just take those out of sample, just randomly split the training data into 3 pieces. Yeah, unless you're doing things such as time series-based prediction. Obviously, if you would dare also do it out of sample, you're going to have models that simply learn how to interpolate between different points within those folds. So there, definitely you can't do that. So also there, your cross-validation needs to be done in an out-of-time fashion. And then there is also a very extreme form of cross-validation, which is called leave one out cross-validation. And in that case, you train, in this overview here, you train as many models as you have instances. Because here, you have as many folds as you have instances, right? So every time you train a model on all of the instances that you have, except one. And you just use that single instance to validate your model with, and you average all of those validations together. According to some people, this has a lot of benefits for reasons that we will see immediately. It also has one apparent drawback. As many models as you have instances, that sounds like a lot of time that will have to be spent in training. So yeah, one of the drawbacks of leave one out cross-validation is that it takes a lot of time, right? Now, why does it have another drawback? Well, to understand that, we need to take a look at another aspect first. And so again, remember, cross-validation is mainly for tuning. The test set is still necessary to perform a real true evaluation. Because with cross-validation, you're repeating over the same data, and you notice that it doesn't work, so you try to expand your hyperparameter grid a little bit, and you bring in more learners, and you try out different processing tricks or featureization tricks. So at the end, it will not offer you ultimate protection. It's only to try to make you a little bit more less exposed from overfitting models. What about pre-processing steps? I told you before that, well, not ideally, but what you have to do is that you don't first pre-process all of your data and then you split it into train and test. No, you figure out what the preprocessors are that you want to integrate in your pipeline on your train data. They're part of the learner. You re-execute them on the test set, right? And we saw things such as if you want to impute with the average value of a column that has missing values, well, then that average value is part of the parameters that you learn effectively. So what about this internal thing that we have going on here? Should we then also say, well, this model applies preprocessors on only these two data sets, for instance, to impute missing values with, and then also applies the parameter that it has learned on the remaining fault? Ideally, yes. Now, in things such as scikit-learn, if you say, well, I have a learning pipeline starting from pre-processing steps and then my actual learner at the end of it, this is rather trivial to do, right? If you take a less pipeline-inspired coding approach, you will often see, yeah, I don't really know how to integrate this, so I will still first pre-process my training data, and then I will cut on that pre-processed full training data. Again, you're introducing a little bit of leakage in that case, right? Things which also sometimes make this hard is, what about these smart sampling techniques that we saw? So what if my data set is widely imbalanced and I want to apply something like SMOTE to increase the number of positives that I have and to remove some of the negatives that I have in this data set? Again, this is something that you learn from data. So ideally, you also use something that can fit itself on trained data only and then be reapplied. Well, in this case, we don't reapply it even on the test set because in the test set, we don't need it. But what inside of cross-validation? Well, there, ideally, you do use a smart sampling technique, again, that only learns from 2 out of the 3 faults and then introduces the synthetic instances based on those learnings in the remaining fault. Again, there, depending on the library that you use, that might be pretty hard to do. So there, I would say, well, it is permissible to say, well, first up or down sample the trained data before you also start creating your faults. That's sometimes a shortcut that we take, right? But again, do keep in mind that this is introducing a little bit of data leakage again. So again, why the test set is pretty much necessary to give that completely unseen, fresh estimate on how well we're actually doing on an out-of-time data set. Now, cross-validation, what this does is it gives, so if you check kind of the theory behind it, it will tell you, it gives a pessimistically biased estimate of performance because most statistical models improve if the training set is made larger. That sounds bad. And then if you read about leave one out cross-validation, it says, well, it's approximately unbiased or as unbiased as you can get because for every model, you're using the whole training data except for one instance, right? So that's the best that you can do to still have some sort of cross-validation going on, but not using all the data just in one single huge bunch of data. So this is approximately unbiased. And every time we talk about bias, we will say, well, bias bad, unbiased good. But here we do need to be a little bit careful because what the term bias here relates to is to one of the 2 sources of errors that happen when you train models, right? And I think already last time I spoke about model complexity and its relationship to bias and variance. Likewise, I told you, well, we saw this with the decision trees that continued to grow in complexity, and they did better and better on the trained data, and they did worse and worse on the validation data. And I told you then, well, for models that you can iteratively train, given that they are complex enough in that case, and given that you have enough data, you can also see the same effect over rounds of training. So also there, they will get better and better at the trained data, but at some point, they will start overfitting, and they will do worse again on the validation data. And the third axis that you could put here at the bottom is size of the data set. So again, given that we have models which are sufficiently complex, and given that we train them for long enough, right, if then I slide over the number of train-in samples that I give it, I will also see, well, if I only have a few samples to train it with, right, it will not overfit the train data at all, right, because I'm only giving it a very small subset of those training samples. As I give it more and more and more and more training data, at some point, it will start overfitting again the trained data, and at some point, it will start doing worse again on the validation set. So basically, either if you have models that can grow in complexity, or models that can grow in terms of iterations of training, and given that these are complex enough, so given complexity and given size, with complexity, given enough training and given size, or I increase the number of train samples that I give you, and again here, given complexity and given rounds of training, right? What I see is a general pattern that if I would look at my error or my loss on my training data, that generally they all start out bad and they will go to 0. And similarly, if I look at loss on a validation set that I would keep track of, right, besides to kind of see at every step, well, now how well is it doing? Well, at first it kind of goes down together, but then at some point it will go back up, right? So every time after this point, we say, well, here we are in the overfitting regime, and that makes us unhappy, right? We don't want to end up there. So if we look at two types of error that we see, well, it's kind of quite easy. We can say, well, one type of error comes from the train data already. And we can there see this kind of pattern. It starts out bad, right? And it goes to 0, given that everything else is large enough, right? So given enough data, given enough time of training, if we can play with the complexity, that will go to 0. And that's called bias. That's this red line on this figure, right? So the red line here says is, well, you have models that are too dumb to even fit the training data, right? So they will do bad on the train data, and obviously if you would give it new data, they would also do bad, right? So in the beginning, that's why this variation loss that I have is also high, right? They are not even capable to fit the general patterns. They don't learn anything at all, right? Or they're generalizable in terms of their dumbness. Yeah, right? They don't give you any unexpected outcomes in the sense of, well, they were dumb on the train data, they remain dumb on the test data. So at least that's a positive, I guess. You have some trust, at least, that you can have there. The variance, that's the other angle. And you see there, that's the blue curve. It doesn't exactly follow my validation loss curve, because what variance says is, this one is more related about the variance in terms of errors that you make, right? It's not directly the error that you make on the validation data itself, but it's more about what's the difference between the error that you were making on the train data versus new data. So that's exactly generalizable. So even if you're dumb, right, the difference between your train loss and your val loss is not that high. So your variance is low, right? But once you start overfitting, well, there again, okay, you do super well on the train data, but you have forgotten anything because you have overfitted so much, right? You've thrown away all of these general patterns, so your variance goes up. So then if we add those two together, you come to this black curve that you see there in the middle. And the black curve will tell you, well, there is then, if you add those together, there is some ideal point here. In terms of, if you have a certain data set, and you can spend a certain time of training, don't go too complex because you will overfit. Don't go too dumb because you will underfit. Your answer is probably somewhere in the middle, and that's what we're looking for. The same would work if we say, well, we have a model with a fixed complexity budget, right? And we have a fixed amount of data that we have, right? How many rounds of training do I do? Well, also there you will see, well, if the model is complex enough, if you continue training and getting those weights better and better, at some point it will also start to overfit, right? The same for size of training data. If I would be able to throw more and more and more trained data at models which are sufficiently complex, and I can train them for long enough, we would also see the same pattern. Yeah? Bias, basically, you can directly interpret that as how well is this model capable to fit the trained data. So how representative is this model sufficiently complex to learn what's in the trained data? That's the bias of the model. Now, this is a very well-known statistical pattern that has been observed in a lot of cases. Very often, we like to put complexity on the bottom axis, but like I said, you have basically 3 choices there, given that the others are sufficient enough. But complexity is typically one that is easiest to play with as a model configurator, because you can either make your decision tree deeper or you can put more parameters in your neural network, so this is easy to explain the picture with. But now, if we think a little bit about in our world as machine learners, and especially with complex models that we use, cross-validation gives a pessimistically biased estimate of performance because you're giving it less training data than you actually have. So what this thing is actually saying is, well, we use the curve not for complexity, but we use it now for size of the training data, number of trained samples. And there we say, well, given that you have a model, well, here you have 2 choices, a model which is not very complex and a model which is very complex. And in both cases, we'll make sure that we train it for long enough, right? In both cases, kind of, but especially like for a model which is complicated enough, if you give that complicated model only a few training examples, right, only one, let's say, in the extreme case, well, we know it's even going to do a horrible job at fitting that one example correctly, right? But as we increase, very often it will kind of, for models which are very complex, they will very quickly go to 0 and then stay there. So here I will kind of show the two extremes. If I would use an incredible simple model, then very often you would see that kind of the bias goes down way more gradually, because I do need a lot of training examples to kind of fit the training, and it will maybe not even ever reach 0 exactly, right? So the middle point is somewhere there, and if my model is really too dumb to fit anything, it will never reach 0 there. Let me increase the axis a bit, whoops. So that's bias. What about variance? Well, for variance, I don't care what I did in cross-validation. Variance I basically obtain in terms of what's your performance on the test set like, and how much does this differ with what I observed during training. So these are the size of training examples that I'm given. The size of my test set stays the same, right? Well, very similar in the starting position. My model hasn't learned anything that well yet. They've got way too few training examples to learn from. So on my test set, it will also do a horrible job. So my curve, my loss curve will also be high. So the difference between these two curves is very low in terms of the variance, the difference between them, right? But then, again, in both cases, you will see that this will start to gradually increase, right? And so on, until at some point it goes too high, right? I shoot over this overfitting or this middle point, because now my model is kind of busy too much with memorizing all that training data, but it's not so good anymore at generalizing. For a dumb model, again, the most dumb case, which is not even capable to fit the training data perfectly, you can kind of imagine that this variance increasing effect will be less outspoken, right? Because it's not even perfectly capable to fit the training data perfectly. So also on that test set, that loss curve will, at some point, will also go back up again, but probably not that much, because it will still remain closer to the train curve. So this is for the very dumb model. This is also for the very dumb model. For a model which is extremely complex, there you will again see the opposite, that from the moment that this thing has started to basically perfectly capture the training data, because I'm using an incredibly high complexity and I'm training it for a long amount of time, already from this moment, my variation will shoot up crazy already, right? So those are the two kind of smart dumb angles that my model behave in. Now, in our situation, to go back to cross-validation, what we're then basically saying is, well, because you're now given less training data to this thing, you're being pushed to the left here, right? You're being pushed to situations where you give a higher biased outcome of your model. The bias is higher, and that's bad. We don't like that. Versus the best thing that you can do is you leave one out, then you're almost close to using all of the training examples that you can, so then you're being pushed to the right, which is better. But you see that it doesn't matter as much in all cases, right? It matters a little bit in terms of, well, how dumb is your model versus how complicated is it. And indeed, if you use very simple parametric linear models, so which in terms of bias, they behave according to this line, right? In that case, you would prefer to be more of around these regions, right, where you use as much training data as possible, because, well, if you cut it in half, you're already giving up a lot of bias there, or you're getting back a lot of bias in that case. But in the case where models are sufficiently complex, if you look at this figure, and you compare it with, and in the case where the number of train instances that you have are pretty large to begin with, which is another thing that 50, 100 years ago, we had 20 instances. Of course, if you would cross-validate them and you cut them into two pieces, you throw away half of the information there, of course your bias is going to shoot up, right? But if you have 2 million instances anyway. So in the case of today, if you think about this, and I would ask you, well, what's actually the biggest challenge, given that you have enough data and models are complex, and we have the compute to spend on training? Is it bias in the final error that we see that will be the major part? or is it variance that will be the hardest to get down? What do you think? What's easy to bring to zero? What's harder to bring to zero of these blue and red lines? Exactly, right? In our regime that we play in today, we are already in a very low bias regime. Even if we cut it in 3 folds, not a big deal. We still have enough data, and our models are complicated enough that they will probably fit those 2 folds out of those 3 quite easily if we want them to. But it's variance. That's the issue, right? We don't want to overshoot to the right-hand side. We're not playing in this world in terms of complexity and sizes. We're playing in this world, right? So leave one out, cross-validation, I would say don't bother. If you use something like an XGBoost or whatever, and you have 1 million instances, you don't do that. You will only end up waiting a long time. The only reason is, but this gives me an unbiased approximation of the error. Screw bias. Whether it's 0 or it's 0.5, I don't really care, right? But the variance is the thing that I care about, right? I care about generalization performance. So for me, actually, I would say 3 folds, 2 folds, 4 folds, and repeat it a bit, but not leave one out. Cross-validation. That's not what we're going to do. Right? This has become, to tell you the regime in deep learning, we can talk a little bit further about that, but to tell you something really crazy in terms of this descent behavior that we see. So in the overall error, you see that there is like a first descent part where both the bias is going down, so bias, and the variance is not increasing too rapidly, right? Until you reach some optimal complexity point, and there we saw, well, the error goes up again, unhappy, unhappy. So we say, well, traditionally we say, well, everything that follows this complexity point, forget about that, worthless, right? We don't want to end up there. That's overfitting. So we basically say, well, all models start out underfitting, and then we make them more complex, or we add in more training data, or we train them for longer to reach the best possible fit that we can, until we start that we are getting too high in complexity, and then we stop. What if I would say, does there exist a regime where I come up with a model which is not just complex, but highly complex, all the way over there? What happens if I end up in that situation? And up until a couple of years ago, everybody believed, well, this black curve to the moon, right? This will never be helpful. You're over-parameterizing. We even know that if you have 5 points that you need to fit, and you would throw a 2 million polynomial at that, with 2 million coefficients, that you have more than one way with that line how you can fit those 4 points, right? You have as many ways as you can dream up of scenario. So of course, extra complexity is not going to help, right? Bias is easy to figure out. Bias at some point will reach 0, and then if you increase complexity further, it's never going to do worse on the training data anymore. It will stay 0, right? What do we see? And this happens for models. There need to be some criteria, because like I said, it's not only about complexity. Basically, at the bottom axis, we have 3 axes. So given sufficiently high complexity, but then also given sufficiently high amount of samples, and given a sufficiently high amount of train time that we can spend. If all 3 happen, then we see that there is actually a second part of this curve where the black line starts to go down again. Why is that? Well, not because bias can go below 0. We're done there. So the only thing that can suddenly magically go down again well, actually, it should follow this line because bias has become 0, right? So I need to draw it like this, sorry, is variance. And this is a strange regime that has been called double descent. And companies such as Anthropic and OpenAI were the first to notice this, because only with modern large language models, where we went into a complexity in the billions of parameters, and data sets with many petabytes scales of text, and budgets to train these things for many weeks, At some point they said, well, what if we just let them train further and further? And it's weird if you think about it, because what do we optimize during training is the train loss, is the bias. You might think, well, at some point you have reached zero. What is there left for the optimizer to optimize on? There are no gradients anymore that happened there. Right? So it took quite some time before people figured out, like, why is this actually going on? And it has to do a lot with the regularization terms that we feed into the loss functions. Yes, there are many different ways how you can get a perfect MSE fit on your training data, but there is still the size of the weights in there as well, which if I would plot them on top of this bias curve, I would make them part of the error. They're not really part of the error, but they're part of the loss function that I train on. Well, these continue to fluctuate. So still during training, there is a small gradient descent that happens on, yeah, but perhaps there are still different ways how I can fit the training data perfectly, but with different values for these weights that I have. Can I still make them smaller and smaller? So in a way, it's like your training now is again trying to, it sounds like we're in a situation where you have a high complexity, yes, in the number of parameters, but in terms of the L1 or L2 norm for our weights, no, we are there actively making them part of the optimization as well. So it says that we're kind of increasing the complexity. We do need to be a little bit careful. Yeah, in number of parameters that we've set, but the values of these parameters are being pushed back closer to zero. And there we find that regimes exist that within still these over-parameterized models, configurations exist that give a perfect fit on the train data and have managed to also bring the results on the validation or test data back down as well. Where does this happen? For none of the tabular data sets that we have, right? We talk about models that are extremely large in complexity and data sets that are extremely large and weeks of training. But this is called double descent, and this phenomena has also been described as grokking behavior, because at this point, your model understands the train data, but it's spending additional time to grok it. And to grok in English means to fundamentally understand something. If you wonder where Elon Musk came up with the name for his LLM called Grok, it was from this, right? In recent years, there have been some publications that have better explained. At first, people didn't really know what was going on there or when this shows up and this doesn't show up. Now we basically fundamentally know that if you would have enough data and enough parameters in your model, you can also see it with tabular data, should you want to, or toy data examples. Basically, what you need to have is, well, like I said, sufficient complexity and some regularization term that you can optimize during your training on. And then you can see it happening. Just goes to show that some of the things we know to be true for many years, suddenly there is another part to it as well. Anyway, what a story. So just to say that for cross-validation, don't be bothered too much by leave one out cross-validation, because typically keeping our bias on the left-hand side and so on, or being afraid that our bias would be too high, it's not something that we really need to be afraid of. We care more about variance. Some additional aspects, multi-class. First of all, you can still make, obviously, a confusion matrix when you are in a multi-class setting, except of it having true positives and true and false negatives and positives. You just now contrast every true class with its predicted class, informative to look at, because you can typically spot like quadrants where things are being confused with one another. My cat looks like a dog, or whatever it is in this case. It's about predicting mental cases in patients. So anxiety looks a lot like depression. And Suicide Watch looks a lot like depression as well. It's probably based on posts on Reddit or something like that and trying to predict in which subreddit that the post was made. Can you still make an ROC curve? At first, well, no, because for an ROC curve, right, I go over every possible threshold. I need the true positive rate and the false positive rate, so I need a positive, right? If I have more than two classes there, I can't do that. Well, yeah, there is a way how you can do that, just by plotting multiple ROC curves. If you have, what is it in this case, 3 classes, right? The turquoise curve at the top for class 0, basically says, well, what if we pretend that class 0 are our positives and the other 2 are negatives? And we slide over the thresholds there. So how good at you are at catching out the 0 cases at the cost of making mistakes, false positives, on the other 2 sides, right? Then you do the same for class 1. Then you get, what is it, the blue curve, or no, the orange curve, and then you do the same for the class 2, which is the middle blue curve 1. And then here, what these 3 curves already tell you is, well, 2 out of these 3 classes are easy to catch out, but for this orange class, class 1, there I'm having some more trouble, right? If you want to still get some overall area under the curve, then what you can do is you can average these curves together. And then very often, when people are averaging these kinds of things, they will propose you 2 types of averaging, either micro-averaging or macro-averaging. Macro basically says, well, first calculate the area under these curves for the 3 curves separately and then just average them together. So you average over the number of classes that you have. Micro-averaging basically says, well, no, you also need to weight it based on the number of instances that you have for these 3 classes. So it's not just 1/3, 1/3, 1/3. It's weighted by the number of instances that you have for these 3 classes. Right? So you can get the 2 views there, and depending on how imbalanced your data set is, remember in the case of class imbalance, that these curves have a tendency to stack up on top of each other in the beginning part of the curve, right? So there, if you take a macro average, it will probably be also wildly different than if you take a micro average where you weigh based on the number of instances as well. But you use one of those 2. There are more than these for multi-class. If you are interested, you can check out a paper where they propose lots of metrics for multi-class classification. This is something that you can take a look at. Still, here also, like a thing to keep into mind is normally with binary, we say it's a positive if my probability is above some value that I picked, my cutoff. Here for multi-class, basically what you typically will get is a probability for each of the 10 classes that I have, right? So sums to 1. How do I then decide the final outcome? Well, typically I will say, well, the one that got the highest probability, that's the class label that I will predict. That's the one that I will assign. But then you typically end up with a quite harsh confusion matrix again, because if my model says, well, I'm 0.51% sure that it's depression and 0.49% sure that it's something else, well, you were pretty close, right? I took your topmost prediction, which was not the correct one, but actually you were pretty close. So you can again say, well, make me some sort of accuracy value, not based on just taking your top-ranked prediction only from that probability vector, but do it over the top k. And that's then called top k accuracy. Top 3 accuracy means, did you get the correct answer within your top-ranked 3 predictions? And if your number of classes goes up, typically it's better to use that, right? Also means that if you have 10 classes, you would calculate a normal accuracy metric, given that you don't have too much class imbalance, and you see something that's closer to 50%, don't be unhappy. The a priori accuracy here is 10%. If we randomly pick a class out of the 10 classes, I have 10% to get it right, right? So there my standing or my base accuracy is not 50%, but it's 10%. So 50% is already a 5 times increase over what a random model would do. So adjust your accuracy or your lift accordingly. If your technique, but this is not very widely or applied in a lot of cases anymore, but you could wonder, okay, what if for some arcane reason my technique does not support multi-class and it can only do binary classification? Which tricks can I apply? And so tricks that exist, they're part of things such as scikit-learn, you can put them in a pipeline as well, is basically the trick boils down to, oh, well, then you just build multiple models. And you have strategies such as 1 versus all and 1 versus 1. 1 versus all basically says, well, for every class, the A class, the B class, and the C class, try to predict whether it's an A or it's not an A. So versus all the rest, right? 1 versus rest. And then if you have a new instance like this triangle, you ask your 3 models what they think, right? So here A versus not A, C versus not C, B versus not B, and you pick the one with the highest probability, which is not very well calibrated, which is a reason why for tens of classes that this starts to work less well, but if you have 3 or 4 classes, this might just work, right? Same 1 versus 1, there you build a model for every pair of classes that you have. Just because here we have 3 classes, the number of pairs is the same as the number of classes that we have. So A versus B, A versus C, and B versus C. Of course, the ordering doesn't play into account here. We again ask every model to predict. Here we expect them to give us a class label, and here it's basically a majority vote that gets standardly utilized. So A, 2 out of 3, the result is A. I still want a probability, okay, 2 out of 3 then, right? And you extract a probability based on that. Also horribly incalibrated, right? Also here you might wonder about, yeah, but these cutoffs, these are probably 0.5, but do they have to be 0.5? Should I not then optimize the cutoff specifically for these submodels, or all things that, yeah, in theory, they are glossed over, or decisions are made there for you, which you can all optimize, but the more that you optimize, the more that you might be doing potentially overfitting things. There exist ways to calibrate this a little bit better, but in a nutshell, you would do this in situations where really you can only use like logistic regression, and it only supports binary classification, and you only have 3 classes and not 1,000 of them. If you have 1,000, it starts to break down, and we'll see that in these cases of majority voting, we have better ensemble-based techniques that we can utilize. Same for multi-label. Again here, for evaluation, there are specific definitions for lots of these things. Like multi-label means you have a picture, you have 10 classes. Which of the 10 classes shows up in here? Not just 1 out of the 10, but more than 1 can show up. So it could even be 0 out of the 10 or all 10 of them. So then typically per class, you again calculate in how many cases did we spot it correctly, and we perform some sort of micro or macro averaging on the class level, where we either average over the number of classes that we have, or we average also over the number of instances that we have per class. So we first, on a per class level, calculate a binary metric again, something like accuracy or F1, or even like an AUC coming from an ROC curve, and then we average that in some way. And then, or we just look at the 10 different values that we get, and we see, well, one of the labels were easy to spot. We can check whether there are cats and dogs in the picture, but on horses, we're not doing so well of a job, right? We always miss that there is a horse in the picture. But again here, what if your technique only supports binary classification? Well, either you transform it and you just again train as many binary classifiers as you have potential labels, 1 for each thing that might show up. So you just have a model that tells you whether there is a cat or dog in the image, or whether there is a cat in the image, sorry. You have a different model that tells you whether there is a dog in the image, yes or no. You have a different model that tells you whether there is a horse in the image, yes or no, and so on for all of the classes that you have. And then if you have a new instance, you just ask each of your models separately what they think for that label. Now, that's easy. That is done quite often. It misses one thing, obviously. And what it misses is potential correlation between the different label outcomes that you have here. There might be a pattern in your data set that informs you that if there is a cat in the image, that it's way less likely that there is also a mouse in the image, for instance, right? So what I would do in the ideal case is build some kind of chain instead, where I say, well, if one of these models, if I could start from a model, for instance, that predicts me whether there is a cat, yes or no, then I can use that model's logic or prediction or probability as a feature in the second model that I'm building. So then the model that predicts is there a mouse in this image can take the prediction of the previous models as features. Then, of course, the question is, yeah, but then in which order are we going to build these models in? Which one should I start with? If you don't have a lot of labels, you can just brute force your way through that, or you might use some statistical techniques to inform you of the ordering that you should apply. And that's then called classifier chaining, and that's implemented in packages such as scikit-ml, but I think it's also nowadays in just a bare bones base scikit distribution as well. What you could also do is transform it into a multi-class problem by making the power set over the label. So let's say you have 3 potential animals that can show up, dog, cat, and duck. Then you say, well, basically I have a multi-class problem where it's either none of them are there, or only dog is there, or only cat is there, or only duck is there, or dog and cat are there together, or dog and duck are there together, or cat and duck are there together, or they're all 3 there. But doing this, you see that it explodes rapidly. If you take the power set of something, you will have a multi-class problem with a whole bunch of classes. Typically, that's less recommended, but again, if you're very limited in terms of labels, might work. But better is to use more stronger methods if you find yourself in a multi-class or a multi-label setting where you have a lot of classes or labels. to come back to this picture, we said, well, the whole reason why we're making life cumbersome for us here is because we want to, well, we know that we will repeat this experiment and we want to avoid going into kind of overfitting positions. We want to be able that we find something of which we at least have some confidence that when we bring it to our test set, it will still be generalizable as well. Now, because this test set might be taken out of time, right, and there might be volatility still in there that we couldn't account for, if our test set does disappoint us, what do we do then? And of course, right, and you're not to be blamed, of course you will say, oops, let me go back to the beginning and let me try out something else, right? Do realize that if you do this, you won't be immediately shot, but do realize that effectively now you're making your test set part of this repeated experiment as well, right? To give you an extreme result, you're playing for the assignment 1 on a competition leaderboard, similar in the style of Kaggle. So you have the train data and the test set you don't know the labels for. Well, just based on brute forcing and reapplying something and checking it out on the test set and seeing how well that you got it, at some point you will get a perfect result on the test set. Right? Proven that you can also, through some weird optimization, get there in the end, which is exactly why Kaggle, and also in assignment 1, why we do not show you the results on the full test set, but we also keep some part hidden in the feedback that we give, right? To then at least keep that as the result that can tell you, no, you optimized 50% of the test set, but you're still very wrong on the other 50% of the test set. But it does show that the idea is not that you revisit the same test set multiple times, but it happens, of course it happens. Now, what you should do is hunt for a new test set, but that's always hard. People don't like to do that, right? Why would you? So be a bit careful to avoid that. Feature engineering should be learned on the train data. I already mentioned this. I think the other things I also mentioned already. What is out of the question, preferably, is not using a test set. Right? And I will show you a couple of cases where that does happen, where you can say, okay, it's fair to do so, is when your data set is really small, or you know that you will be using heavily biased models anyway, very simple parametric models, which do not tend to overfit train data so much to begin with. So, and again, if your scores are still too good to be true, even on your test set, if you get 99% AUC, do check for data leakage. If you still have data leakage in your test set, you will not be protected. So to talk a little bit about, what if I have too little data available? Well, the extreme point is I have more features than instances. Well, forget about it, right? Throw away features as much as you can. That's never really a situation that you want to end up with machine learning, right? And any model can fit the training data quite trivially. If you're not yet in that regime, but you don't have a lot of instances anyway, then what you do see that happens, or what you can apply if you still want to configure or tune models, is that you do your cross-validation, you don't have a test set anymore, but you use these average cross-validation values that come out of here to tell you how well you're doing. And look, the model configuration where we used our technique does better than the model configurations for these other techniques. That's something then that you can do. A lot of papers do it in this way. I hate that practice personally, because cross-validation, again, is to tune models. You haven't really performed a real test in that case, right? Who is the guarantees there in terms of really having learned generalizable patterns, or way less? And again, here, it depends also heavily on the hyperparameter configuration that you're running over. If your competitors, if you restrict their hyperparameter ranges to be a bit smaller, and for your proposed technique you go, we try everything, isn't it normal that you would find a configuration that works best there on the training data anyway, right? Does it still do so on a test set? You really didn't prove that then in that case. But papers do that quite often, but be a bit careful. This is something you would limit ideally then the number of configurations that you test or that you tune with one another, I should say. If you have way less data, you can fit on the training data only and you're back in statistics land. Stick to heavily biased, simple, linear parametric models, and typically there you will also see that you're back to the metrics that tell you something about the goodness of fit on the train data, right? But again, you didn't really perform a real test. So the test set is there to really prove, is this model going to be applicable in a real inference setting? So do keep that in mind, that these are really two different things. What about unsupervised models? Of course, there you have also metrics, but they are way more subjective, right? Because either they're based on still having some sort of true label being there anyway, like you're doing a clustering. Is this clustering solution good or not? Well, either you compare that with what we know the true groups are, but who is to say if you find an alternative grouping that that is not a good grouping, right? There are potentially multiple ways to group people, right? If I expect an outcome based on gender of students in my class, well, I might have performed a different grouping based on age, right? Who is to say that one is better than the other? It's just two potential groupings. So what does it make, or what does it mean for a clustering solution to match that true label that you've set? So typically what's done instead is to, exploit some intrinsic property of the data, where we say, well, a good grouping is where the people in the group, they are similar to one another, and the groups themselves, they're dissimilar to one another. But again, it heavily there depends on, but how many groups are you creating, right? You can also always drive those inherent metrics that you use for evaluation to zero, because they're very often closely linked to the metrics that the technique itself is also utilizing to optimize with. Right? So they're kind of linked to one another. If you evaluate based on the same thing that you utilize to optimize a solution for, it's probably easy to reach a good result there in that case. What about a test set? Very often, if you just use unsupervised techniques or some sort of descriptive report or exploration of your data, we don't even bother with a test set. That being said, if you do use unsupervised techniques, to make them part of your pre-processing pipeline in some way, because you say, oh, I'm going to do a clustering on my data, and then I will get features based on that. For instance, what was the cluster that every instance was put in, and what's the distance between that instance and its cluster centroid, or even to all the cluster centroids? Well, then you better make sure that you pick an unsupervised technique which can also fit itself on a piece of trained data, and then without re-establishing the full clustering or having to relearn the full clustering, reapply those features on new instances as well, right? And for k-means, that would mean that you, for instance, you have a new instance, you take the centroids that you obtained from your trained data and you use that to assign and to calculate the distances. You will not recalculate your clustering solution. And then indeed, you might still pick things that are maybe overfitting on the trained data, but again, the test set is there then in that case to rather check whether this unsupervised step in your pipeline that you're using for featureization, whether that's not blowing up on unseen data in some way. Now, the test set is basically the first check that we do to see how well is our model doing in inference. Ideally, it doesn't stop there. Once the model does get deployed and does get utilized, typically you continue also to monitor it, to continue to check whether it's still doing well today, right? That's hard to see if you just get probabilities on individual instances. Models will be very happy to continue to do that. Even if new missing values or new levels show up, there will be patches in place to kind of avoid them from completely crashing down. So you will get probabilities. But are these probabilities still as useful as they were back when we tested out our model for the very first time, right? So what happens is your model bases itself on a reality that it extracted from your trained data. Meanwhile, your data distributions are shifting around all the time. Right? So just as we said, well, we should make sure that we are not extrapolating outside of the bounds of our training data, right? Well, who is to say that maybe tomorrow all of the cases that we receive have already shifted to be more over here rather than to be more over there. And those are the things and typically that you would have to monitor for. Like, is my model still, does the representation that it has in its head in terms of what data looks like, does it actually still match the reality of the data that we see today? Now, typically how that's done is by setting up a whole slew of monitoring metrics that you utilize. And they range from simple things such as, for every feature, take the distribution of age today for the last 2 months that we saw and compare that to the distribution that we saw in the training data. Is that shifting too much? Warning sign. Or the bounds of every feature still the same? If not, warning sign. On the side of model outputs, or the cumulative probability distributions for the last 100 positives and the last 100 negatives that we saw, or that we got out from the model, or are they still equivalent to what we saw back when we trained this model, right? Or new levels appearing for categoricals, or new missing values appearing. All of these things should pop off more and more warning lights that tell you at some point it's time to retrain this model, or to take it out of commission, because apparently the reality has changed too much based on back when you trained this model. And very often in organizations, when companies have a whole factory of models, a whole warehouse of models, and for most of which they see not a lot of usage anymore, well, the answer is simple. Why not? Well, we don't really trust the predictions anymore. They're not so good. Weird, if I check the documentation, right? At that time it was tested, it was a good model. Well, why is that? Because that was 8 years ago. Between now and then, you have new products, you have new promotions, you have new pandemics, you have new wars, you have whatever. Maybe it's time to retrain that model, right? Or maybe just to block it off and say, well, don't use it anymore, it's become too old, right? So there is not such a thing as a continuously self-learning model, right? Unless you manually put in a retraining loop where you say, well, oh, I can say something about that as well. Is it time for me to yap about that? Yeah, kind of, I can yap about that now. So what most consulting companies have ended up doing to mitigate this issue is to say, aha, we know this is a problem, right? Models become outdated over time. They don't stay fresh forever. And because the reality of your data changes, and of course, managers love to hear that. Yeah, we live in a very volatile situation. For us, things change every day. That's the only constant is change. You put it on a slide with a tree behind it, and they will love that. So what can you do? You say, okay, feature snapshot. I know that's based on 2 months back. I need to predict something 1 month in the future, right? I test that out, happy on my train data. Then during testing, I'm going to check, okay, how fresh does this approach now work? So to today is somewhere over here, right? So I can move forward a bit. So I take a new feature snapshot. So here I have trained my model, and then I'm going to test it out. So a new feature set of my customer base, new targets. I apply my model to predict. It's lower. Oh, damn. It's going down pretty rapidly, but it's still okay to use a month later after it was trained, right? I slide forward a little bit again, right? Or I would monitor even in production, or let's say I'm still playing around, so I'm not at my today point yet, so I can repeat that because I want to get another idea about the volatility. Wow, now it's way lower. My model is basically predicting randomness right now. Aha, what does that mean? Well, you're predicting some sort of price outcome, right, for the stock market or whatever crypto that you're doing, and you see, well, based on what I saw 3 months ago, I can predict what happened a month after that, but if I try to predict something 2 months further, it's already not working anymore, right? And it's not even that you're trying to have a model that outputs both an output for 1 month from today and 2 months from today. It is no, based on the last month, tell me what will happen next month, and then a month later, based on that last month, so you do get the most recent information, predict me what happens a month later. And already then it starts to work less well. So already those patterns are not generalizable. So we check that out, we do that backtesting, and we see, ooh, this degrades very rapidly. Solution, automated retraining. Right? We will perform an automated maintenance, we put in a cron job, no, that's old-fashioned. We use continuous integration and deployment practices with a GitHub action, where every 2 months, we will say, well, this whole development script that we have that produced this trained version of this model, retrain the model. So every 2 months, extract the data set and targets and make a new trained version of that model, version 2, version 3, version 4, that you will every so often keep up to date. Ah, look, now it works much better. If we backtest this strategy, if they do that, in many cases not even, right, this works. So this means you have a model that uses the most recent 2 months of information to predict what will happen next month, and every 4 months, you're retraining that whole thing, right? Okay, but now what you have done, if you don't test this correctly, that kind of retraining thing that you're doing there, actually this has become part of your model, of your learner itself. So you should not just test now the fact that a singular trained version of your model degrades rapidly, but now also this strategy that you have here. How long does that remain viable? For instance, if your volatility as it is on a second order level, now today, for instance, you said, well, every 2 months we retrain our model. What if the rate of your change starts to accelerate? And in fact, now you should retrain to still try that approach out every month, every week. Did you test that? No. So who is to say that this 2-month periodic retraining, that is going to remain viable? Also, that retraining is based on some kind of Python script that you have written. That retraining is not automatically going to change certain pre-processing and featureization strategies that you have put in place. Who is to say that those remain okay a year from now, right? If anyway you have so much volatility. So even if you do that, might be that even your model that you're retraining every 2 months, that every new version, not only it was crap before, but at least we gave it an update. No, it was bad and it remains bad. Right? So actually you're making the correct testing of something like this way more difficult than it has to be. What might be better in a situation like that is, well, on the one hand, this typically reveals that you're using features that are perhaps not the best choices, and you should think more in terms of creating more stable features at the cost of accuracy, but at the benefit of maybe a longer, stable guarantee for that lower accuracy level that you can keep in place for a bit longer. Maybe the duration of your recent information, maybe it's too long, maybe it's too short, maybe you should also play with that instead. Or maybe you're trying to predict some kind of signal in noise for which actually it is not really viable to predict anything in, right? Of course, that is never a good solution to put at a board meeting presentation, so instead you sell this, right? But again, you know what you're doing there. Now, of course, the big engineering firms like Google and so on, they're the first then to talk about papers such as what's your ML test score or hidden technical debt in machine learning systems. So they have felt all of these issues, but there's still a lot of money that you can make in companies that have not realized this yet. But obviously, this is what is happening. Platforms as a solution, then we stop with this part and we go for a break. Yeah, they help to make the monitoring easier at least and to put these metrics into place. A lot of platforms before this started to become kind of a bit more common knowledge were heavily focused on the development cycle. Can we collaborate in code? Can we set up a hyperparameter tuning run on a whole grid and distribute that over different machines and do AutoML? All fun, but once a model is deployed, who monitors it then? Does anybody look at that? Do we monitor the metrics that I just described? And so there we do see that we have like a lot of platforms that have popped up to offer solutions, which is a good thing, right? And the reason is not to make this into a marketing slide, I just picked one, but is to kind of focus on the things that they are kind of checking, right? So tracking of input parameters, caching of pipeline steps, versioning of not only model, but maybe also of data. Can we reproduce this? Can we check output distributions that models give over time? So can we pop up those warning lights that tells you or that tell you that it's time to retrain? Monolabs is another thing. So act on model bias, detect concept drift, and concept drift is a terminology that gets oftentimes used to say, well, the data that you have today that you're actually using your model on has drifted from the data as back when you trained your model, right? So your model is not really working with the same assumptions anymore as back when you trained it. This is more like an open source offering. Again, these are not rocket science things. It's about measuring the difference in KL divergence between two distributions for all the features and so on over time and having metrics on top of that and reports on top of that. But it is helpful, right? So evaluation doesn't stop preferably after the test set. It's something that you need to continue to do. This is NanyML, another player. You can see that they all more or less kind of do the same thing, right? So they show the drift of a certain metric over time to kind of say at some point, well, your model starts to become worse at this metric based on the last 100 predictions that it made, right? The best thing there to do is also to say, well, the best evaluation is not just to compare distributions in terms of input data and output data, but also to effectively retest your model. So that would mean that, and this is tricky, that from time to time, you go to your model, you say, okay, what were the last 1,000 predictions that you gave? And give me the lowest 5 and the highest 5. And I go check manually, was this now indeed a yes case or a no case? That's hard for two reasons. The first reason is because companies very often act on top rank scores only. They only want the top 10 and they call those customers, or they send them a promotion, or they think it's fraud and they do a check or whatever, they do something with it, the whole bunch of probabilities, as we saw after that, as we saw last time, oftentimes just get ignored. So all the shifts that happen there, if you don't do spot checks, right, you won't really catch them. And typically, who has time to look at those boring cases? You won't do that. Second is, and this is a more nuanced managerial thing, but the thing is that once you have put a model in place, which is trained on data that was created before the model was there, that obviously all the actions that you then undertake as a result of those models' predictions on your new data, that they are themselves very likely already changing the behavior of whatever the instance is that you're working with. So it's almost, it is not almost, the usage of the model itself in practice will itself automatically already lead to concept drift happening. For instance, because you have a better model, you start spotting more fraud cases correctly, your fraud cases decline, maybe the way how your fraudsters try to circumvent shifts. So automatically also, just because of usage of your model will make itself outdated by that. That's tricky to get right, and it's very far away from the technical aspects, but this is exactly challenging things to solve in the practical case. Good. That brings us perhaps then to interpretability, but first we will go for a 15-minute break. Okay. So then we can switch our attention to interpretability. So we have already seen, and we will see also, that some models are said to be white box models, as they are often called, and white box meaning that they are interpretable by construction or by design, more like a transparent box, if you will, where the typical limited complexity of the model and the assumptions in terms of parametric design of the model, like linear models, or even things like a decision tree, for instance, which if you don't build them too large, you can easily inspect them, see what's going on. You can easily answer questions such as what are important features that this thing utilized, either based on the size of the coefficients or weights, or based on whether they pop up and where they pop up in the decision tree, for instance, and also to which extent that they drive the outcome for a certain instance. So if interpretability is of a concern, if not only you care about a good accuracy or AUC or something like that, but you also need to kind of have a conversation about how these models actually work, that's still the easiest way, obviously, to get there. Apart from these ones, we also have decision rules. We have things like rule fit, Bayesian techniques, packages like scope rules. They all try to construct models that are by themselves easy to understand. Maybe not easy to understand in terms of how they construct a model, but at least easy to understand in terms of what that trained or fitted model then looks like. Some models are not. These we typically call the black box models. And yeah, once your complexity gets to a certain degree, like in the case of tree ensemble models, where you don't build a single decision tree, as we'll see next time, but you build 100 decision trees and you let them work together, your interpretability already takes a hit. Or if you would be playing with artificial neural networks with a lot of parameters, same thing, then it's not so apparent anymore how every input gets constructed to reach some sort of output value. Now, that's annoying because, well, in a lot of cases, people will say, well, there is a trade-off. The higher you want to go in terms of interpretability, the less the performance will be that you can reach with those sort of models, especially on more complex data sets that we want to utilize. So it seems like it's one or the other. So very often what we end up reaching for is we pick models that have a certain extent or degree of complexity, but then afterwards we still apply techniques to open them up a little bit. So to open up that black box that we have constructed here so that we can understand a bit in terms of how it's making its predictions or constructing its predictions. There are different classes of techniques. The categorization is not perfect by any means, but typically when people talk about interpretability in terms of what they want to do, is typically the same style of questions are being asked. So either this is a complicated model and I want to simplify the model as a whole so that I can understand the whole model in one go a little bit easier, or try to communicate that model a bit easier. Or I would like to get an idea of which features are important, but that's probably not enough. Not only do I want to know which features are important, but also how do they drive the prediction. If age goes up, what happens to my predicted probability? And maybe that's a nonlinear thing that I want to see there for these complicated models. And also, if I look then at specific instances, why did an instance get the prediction that it gets? Like your model says that it's 0.7 probability outcome, but I don't agree. I think it should be way lower, right? Or I do agree, but I want to know why, right? So then I'm looking at specific instances. And generally, you have model-specific approaches that are highly linked to the workings of the actual learner or the type of model that we get from the actual learner. Like if I say, okay, we can inspect decision trees, and what I could do is I could track the position in terms of depth in the tree where every feature gets utilized. That only works if you have some sort of depth and trees going on. With other models, that approach would not work. So the more interesting question that this field is concerned about is, are there also model agnostic techniques that we can apply? So no matter the model that you have utilized, as long as we give it inputs on the one end, we give it certain feature information, and it gives it an output on the other end, can we explain that model? Can we answer these questions that we have asked? Now we'll focus on standard tabular techniques and from an agnostic perspective, but later when we introduce deep learning, we'll also go a bit further on this interpretability part. So here you can see a couple of model-specific techniques, right? So again, very often linked to decision trees, so I can tally which variable was used, and even for tree ensembles that works, because then I can do this for every tree that I have, like when did this variable show up? And also, when it got used, there is a split point associated with that, like if it's lower or equal to this, you go left. If it's higher, you go right. I could also tally that and then show that in a histogram and say, well, this feature, for instance, got used often, and this was the most, or these were the most common split points that appeared. And if you look at this from your domain intuition, dear user, does this make sense that this is an important feature and that this is a split point that seems to show up quite often? Okay, yeah, maybe it does, and then you get a bit more trust, maybe it doesn't. Okay, a bit more general. If we then extend this and we ask in general, okay, I have some sort of model and I want to know which of the features are important. So model-specific could also be like for a linear regression model or logistic regression or even a multi-layer perceptron with only one layer. I could inspect the size of my coefficients, but again, for deeper models, for more complicated models, those patterns are not so easy to extract anymore. So from a model agnostic viewpoint, give me a ranking of the most important features, from most important to least important. And there are different techniques available to us there, like the position in the tree I already mentioned, but that's model specific, so I don't really want that. Based on the mean decrease in impurity, well, that's another idea, and very often when you get these sort of feature importance plots from any tree-based implementation, be a bit careful because this might still be the default approach that they utilize, which it's not such a good default. It's been shown to be heavily biased in a lot of cases. Here it's based on, well, whenever this feature did pop up in one of our decision trees, what was the gain that it led to? Like the information gain that it gave us, right? So what's the degree in impurity that it obtained us? And the higher the improvement that it made, well, the more of an important feature that this must have been. But doesn't really work so well in practice. There's a whole paper that goes over the reasons there that even shows, okay, let's do a test. Let's just add in a random feature, for instance. Then you would expect that this would show up all the way at the bottom, right? But it's not really the case because once you're in the top levels of your tree, even due to randomness, it might be the case that this random feature is actually the best one. Remember our information gain situation where we might have, these are unstable learners, many candidates that are more or less capable to give an equivalent split, right? So even if that random feature gets chosen a couple of times and there turns out to be a splitting point that tends to do relatively well, it will already show up a bit higher in that importance ranking. Just the fact that that feature has different values already makes that it can sometimes be utilized and chosen as a feature in the construction of our trees. Especially if you introduce more randomness in the building of our trees, then also that feature being picked in one of the trees has a higher likelihood. Compared to a feature which is just a constant, for instance, that will never get chosen because that one we can't even utilize to split our instances into two groups. So in that case, a random feature can be more informative or more important in this interpretation than a constant feature is. So that also doesn't really work. Now, there is a very simple system that you could think of that would be ideal, in fact, which would be drop feature importance. And that says, okay, take your favorite metric again, like area under the ROC curve. You have your model, and we test it out, let's say on our test set, your fully trained model. What is the AUC that you get? 90%. And then feature by feature, we train a new version of that model with all the features remaining, except for the one that we kick out, that we drop out. We calculate the AUC again, and then the drop of performance from the original metric value to the one of the model where I kicked out a particular feature tells me something about the importance of that feature. If I remove a certain feature and my performance suddenly degrades heavily, probably means that this is an important feature. That would be nice, but it does require retraining all of those different versions of my model, right? Which is not only slow, but then also, yeah, if I'm doing that on the same train data, I need to set up the same pre-processing strategy. So it's a bit nasty to set it up in practice. So is there a way how we could simulate or try to estimate the effect of a feature being dropped from my model without actually having to drop the feature and retrain the model altogether? And that's what permutation feature importance tries to do. So this one is also model agnostic. And the idea is very simple and is by no means always perfect, but it's still kind of the best approach that we have. You will see that for a lot of interpretability techniques, they will use permutation strategies in some way in their engine or in their way of working. So what does this say? Again, it says, well, you have your original data set, you have your predicted values. This is a test set, for instance, or maybe a train set, who knows, maybe both are valuable. We'll see that in a second. We calculate AUC, and then instead of for every feature dropping that out and training a new version of my model, so my first feature is recency here, or R, I'm going to permute it. And to permute this feature just means, well, across your instances in this batch of data that you have, just shuffle it around. And that is as if I would be breaking up that information there, as if I'm randomizing that information, right? So I'm shuffling that around. It is as if I would be kind of dropping that feature. I calculate the AUC again, and this gives me some importance value for this recency feature. And then I do it again for F, for M, for H, and so on. This does take interaction effects into account, because let's say that this feature is in an interaction with another feature, because I'm just permuting one of them, right? I'm also breaking up its interaction effects that might be present with another feature. So this gives me a measure of importance, not just for recency on its own, but also recency as it's involved in all of its interactions with other features as well. Now, this does tell me then at the end I can make a ranking which features are important, but not yet why they are important or how they drive the prediction. So that will be my next step. What you can then also do is you say, well, now that I typically will get like a figure like this one then, if I know the top 5 of my features that are the most important ones, why wouldn't I just retrain a model with those top 5 anyway? I get a model that's probably a bit easier to maintain, which is sometimes done, and the Boruta package in R was actually one of the first to kind of pop up with that idea and implemented this, but this is something that indeed, if you want to, you can also use this to guide some sort of final feature selection step as well. If you don't like the fact that permuting a single feature breaks up interaction effects, and you really want to see the contribution of recency on its own versus the contribution of recency as it's participating in interactions, you can also go a step further in terms of the permutations that you apply. So you can permute multiple features at once to zoom in on these interaction effects. So now if I take both R and F together, for instance, I can permute these two columns that I have here, and then I can make a choice in terms of how I want to permute them. Either I permute them in such a way where these two values for R and F still stick to one another. Like I had 4 and 13 here, I have 4 and 13 here. I've swapped their place, but the values are still together, right? So now, if R and F would be in an interaction, I'm at least keeping in that interaction importance in my model, right? So, and then by contrasting that with the score that I get for R alone and for F alone, I can kind of try to squeeze out those interaction effects. That's not commonly done because computationally it leads to way more pairs that you need to have to permute and maybe even triplets in some cases. So you don't see that quite often. Typically, you just do it feature by feature, but it is possible to permute multiple features at once. You can also decide, and that might also be interesting, to, instead of what I did here, to at least keep R and F together, to just permute multiple features, but one by one. Like I take this column and I shuffle it a little bit as well, and I take this one and I shuffle it a little bit on its own. Why is that important? Well, that's related to some nasty aspect that can bother a lot of these interpretability techniques that we utilize based on permutations, and that has to do with correlation effects. So let's say in this case that R and F are heavily correlated with one another. For some reason, right? But their correlation is very high. And my model, again, has a certain complexity. It's a deep learning model. I've used dropout, or I have a tree ensemble technique with randomization, so something like a random forest. And I apply my permutation strategy on R alone, and I'm kind of trying to assess, okay, what's the drop in AUC if I permute this feature? And I might get an effect which is maybe a bit less than I expected. I say, okay, well, fine. I then do the same thing for F, and also the effect is perhaps less than I expected. And then I do the same thing for M, and there the effect is way larger. Well, what can be bothering me then, if I do it this way, is what can happen in the case where indeed R and F are heavily correlated with one another. If then I permute R on its own, but I keep the information for F intact, my model will not feel as hampered because it probably has built-in alternative pathways where sometimes it randomly picked R, and other cases it randomly picked F. In the case of tree ensembles, that's exactly what can happen, but also in the case where you train neural networks with things such as dropout, it also aims to build redundant pathways to increase its robustness, to basically also regularize themselves to shocks in just one element in your feature space. Now, if we then use that to assess the drop in performance by just permuting one feature on its own, it will seem as things are not so bad as they actually are. So the question we could then ask is, well, what if we permute both R and F together in one go? We permute the first column and the second column. Well, then suddenly, if I look at my drop in performance, I might see that it's actually way higher, and probably kind of more or less the sum of these two together. So sometimes these, or what more recent packages will do automatically, but what you can check for manually is before you make a plot like this, and before you go, the ones at the bottom, they don't matter at all, so I can just kick them out, also inspect your correlation plot. And based on that, for the features that you find that are heavily correlated with one another, permute them together and show them together in this plot, because you should permute them together and drop them out together. Also, drop feature importance would be suffering from the same issue. So this is already described in this link that I put on the slide. So this is the aspect of the random feature, like why does random pop up so high? So this is if you use the not the permuting or permutation-based strategy, but you use like another strategy that used to be the default one in scikit-learn, but now the newer ones are also available, right? What you there also see is for things such as longitude and latitude, that maybe perhaps both of them uniformly get assigned a bit less importance than we expected, because longitude and latitude are also, in many countries, there is also correlation effect that goes on there, that if you go higher in the north axis, maybe you also go higher in the west axis or whatever. Like if you look at the map of Belgium, there is some correlation effects that are present there. So what you can do is something like this, right, where you either first look at your correlation plot manually or use newer versions, or you make sure to check the documentation correctly, and where you end up with plots such as these that will tell you automatically, yeah, but be careful, latitude and longitude, they're heavily correlated, so you permute both of them at once, and then you take their drop in performance, and that's what you use to rank them. And likewise, both the beds per price and the bedrooms, obviously those are also correlated, right? Beds per price and bedrooms, more or less the same thing. And those three features that you see, price to median beds, bed baths, and price, are also heavily correlated. So you group your features and you permute them. Now, do you do this kind of ranking based on results that you get on your train data or based on results that you get on your test data? Well, both are viable, in fact. We're not really trying to evaluate or trying to inspect in some way our model, so both have their use in this case. The test set will be in line with your evaluation concerns, so with your generalization concerns. So if you see heavy differences, for instance, between the features that show up to be important in your train data versus your test data, this already will reveal that probably some underlying data shifts have happened there. You expect them to be more or less the same, or at least for the features that were important in the train data to remain important in the test data. So it's a good check or a good idea to compare both. But then still, why do it on the train set? Well, another reason is to learn how the model has actually relied on each feature. A question that you might, I thought I had the example in there, but obviously, or do I have it later? Then it's easier to explain with, yeah, I will do it there. But there is a difference. You could say, well, what we have here, wouldn't we be able to do this just by going or by counting things from the data set directly? Like we do have the target there, yes or no, in my train data. I can, even with some kind of simple uniform or correlations between the target and the features that I have, doesn't this give me exactly the same plot as the one that I would get here, just based on the strength of the correlation between each feature and the target that I have here? Not always, right? Because then you do it very often in a uniform or in a univariate, I should say, not uniform, in a univariate manner, feature by feature, versus here you extract it based on all these interaction effects that are present in your model as well, and probably all of these nonlinear effects that are present in your model as well, right? You directly let the model drive, like if I take this away, how do your predictions suffer from it, including all these complex patterns that you have built up over the feature space. Now we'll come back to that example in a second, but let's say now from my plot, I see H shows up high ranked as a very important feature. It doesn't tell me a lot yet. Why? Like now if I would play with H, what happens with my predictions according to this model that I have here? Well, then you can switch to another application or another strategy, another technique, which is called a partial dependence plot. And what it does on the x-axis, we take one feature, but we can do it with multiple as well. It's more readable if we only use one feature, but we could take two and make some sort of contour plot instead. But here we are zooming in on H and H on its own. And I slide a value for H either between its minimally observed value and its maximally observed value, or I just pick the distinct H values that I saw in my data set, and I just slide over those distinct values. So those are the tick marks that you see on this H over there. And then I will try to get some kind of, okay, what's the average predicted probability if H would be this value? And here that's just one average line, but I can maybe also plot confidence intervals then around that. And then you can see an effect, okay, H, if you start from being 0 years old, your predicted probability starts here. Then as you get a bit older, it drops, right? Maybe a risk of some rare disease or cancer maybe. So at this age, you're the lowest risk. But then as you get older, you reach your highest level gradually again. So nonlinear, right? There is like a U effect and then a plateau that gets reached. So how do we build that? We have two ways. Again, a permutation-based way and what you could call an average Joe or an imputation-based way. So the first option to build this plot is you say, well, for H, which is the feature that I'm currently inspecting, I'm going to keep that in my data set as it is. So I'm not going to change any of the ages. But for all of the other features that I have, I'm going to pretend like everybody is just a copy of the average, except for H. So all the other features you impute with their typically median value, but you can take the average as well. You pick something there. You impute with the median to make it a bit more robust, let's say, and the medium typically from the train data, if possible, but doesn't matter that much in this case. For categorical values, we replace them with the most occurring level or the mode. So we have copies of exactly the same person except for age. And we ask our model to predict. Now, we might have multiple copies here sharing the same age, but obviously our model is not stochastic, so we will get the same prediction. So for every age value, given that the rest is average, we know the predicted probability of my model, and we just plot that over there. So that's one way. The second way is to say, well, for each of the age values that you have, right, you're going to create some synthetic instances. And how? Well, you're going to make a copy of the instances that you have. So the first one has recency 2, the second one has recency 4, and so on. But you're going to give all of those members in that copy the value of, well, what if now all of the instances would be of the age 28? So here I change the ages. And then I create another copy, but now with age equal to, I don't know what the next value is, 32. And then another copy for 42. And then another copy, so I expand my data set this way. And again, either by looking at the actual values of age that I have, or by sliding age between some minimum and maximum range. So here I'm not creating average cases except for age. Here I'm saying, well, take everybody as is, but make a copy where I put all of your age to 28, and then to 29, and then to 30, and I ask my model what it thinks. The nice benefit of doing it this way is that now, of course, for the same age value, you will get different probabilities. So you get a better idea of spread happening of there or different interactions that might pop up. Now, to plot it in an easy way, we can just average the prediction per group of age or per value of age, and we can again plot something similar like we did before. Now, we can do that for every feature separately, but we can also combine that, and combining would mean that in this case I keep 2 features as is, and I make the rest average. In this case, it just means that I go over all possible grid points out of these 2 dimensions that I have. So for every value for age plus gender, make a block copy of the instances that I have and put them all to male 28, and then female 28, and then male 29, and then female 29, and you just put points in your contour map like that, and you average the predictions per block. And typically the benefit of being capable to do it is that you will be able to spot interaction effects a bit better. Like here it seems like the average occupation feature has a way stronger effect than the house age does. Like, okay, there is some movement there, but it doesn't move that much based on whether the age is very low or the age is very high. So it might seem that this is a way more important feature than the one I have over there, right, according to the partial dependence plot. But that's not always the case. And if you did the previous step, you might already be warned for this, because it might have told you, well, both average occupation and the house age show up as being important features at the top of this ranking, right? But the partial dependence plot for house age kind of tells you, but the effect is not so high. What does that mean? Again, it has to do with interaction effects, right? So remember that if I permute both separately, it also breaks the interaction effect. So maybe house age on its own does not change that much or does not have that much effect, right? But maybe when it's in an interaction with something else, it does have a more important effect. And that can get hidden away by just creating this average line in your partial dependence plot in a univariate manner. If I combine both, you already get a better idea of what's going on. Like if I look at average occupation now, given a house age, right, I expect to start from a high value, so I'm in the yellow zone, and I will, as I go to 4, I will gradually decrease. And I see that no matter what my house age is, right, that this is indeed the case. Except for ages that are a bit lower, there the effect here is already a bit less pronounced, so there is some interaction going on. And likewise, if I take a value for my average occupation, indeed for this case, which might be the majority case, right, if I slide over my house age, the effect is basically nothing until houses get very old, right? Then the probability goes up a little bit. But if I would have average occupations more towards the 2 side, well, then suddenly also, as I slide over house age, the effect becomes more pronounced, right? If I wash all of the house age effects out over the axis of average occupation, and I average over this axis, I do end up with this average line, but the line might be higher or going lower, right, depending on what the average occupation actually is. So that's the interaction that can get hidden away if you do it in a univariate sense. So for partial dependence plots, absence of evidence does not mean that you have evidence of absence, right? So either bring in more than one feature to show that, or let the feature importance ranking, because there the interaction effects are broken up, guide you in terms of which two features you should try putting on a contour map rather than looking at them individually. So if you ever see a flat partial dependence plot, but the feature does show up to be a very high important one over here, probably something like that is going on. Right? If you average that out, that effect, not much happens. So meaning that the effect can be in extreme cases, can be a very upwards effect for some part of your instances and a very downwards effect for another group of your instances. If you average that out, you get a horizontal line. So rather than making these contour plots, is there something else that we can apply, right? And indeed there is, and the strategy lies, well, in the fact that now for every value of age, or for every value of house age in this case, right, we averaged it together per block that we had here. But why can't we just plot all the lines individually instead? And that would also give us a more detailed view on that. And that's what we're going to do in a second from now. So it uses option 2. You can't do this with option 1. So to do this, you need option 2 to have built your partial dependence plot first, because then you get different predictions because you're copying the same instance for the different values of the feature under observation that you have. We'll immediately see what that looks like. So again, for an example where x0 and x1 are in an extreme interaction, in the partial dependence plots, it might seem that their effect is less than if I look at x2 by itself. But if I put these two in a contour map, suddenly I might see, oh yeah, I do see the interaction there. Or it might be that in your feature importance that both x0 and x1 are higher ranked than x2, even though here it seems to be the opposite case. But this is not too bad, because we will utilize this, as I said. And to come back to the point of, yeah, why do we do this? If you now go, but wait a second, couldn't I just look at the data itself to assess the impact on an outcome? For instance, you have age, so we can put that again on your y-axis that you're observing here. There are different values for age that you have. And then for every value, or for every bin of values, whatever, you look in your train data and just tell me the percentage of yes cases, right? And you will see your effect. Younger age, low percentage, higher percentage, higher percentage, higher, and then it goes down again. If you plot a line through there, well, that's your partial dependence, right? That's the effect of age on the outcome, taken straight from the data, no model necessary. If I then build a model, and my model, the extreme case where age on its own has zero effect and only in its interaction has an effect, that will obviously not appear, but let's say that there is an interaction going on. There you might see you get something very similar, but the effect is way less pronounced than you saw taking it from the data itself. Now, why is that? Shouldn't it be the same, right? Well, no, because when you take it from your data, of course, you use it from the instances as they are. So this shows you the partial dependence not just for age on its own, but also age as it's interacting with all of the other variables that you have. Versus here, you really separated out the partial dependence, the contribution of age alone, right? So if you do see differences, it might probably mean that it's more the interaction between two things that explain an effect, rather than age on its own being sufficient to explain the effect. This is what this would tell you. And so, for instance, you see that sales drop for customers between 30 and 40 years old, right? That's what the data tells you. And in the partial dependence plot, it says, well, no, it stays constant, right? Well, that means that age alone is not a sufficient explanation. Maybe because you have certain products or your whole customer base focuses specifically on people that are younger than 30 years old, and you don't have as many popular products for people between 30 and 40 years old. So yes, in your data, your sales drop, But what the model tells you is like, yeah, but age is not really sufficient. It's also the type of products that you sell to each customer, and that age group doesn't get the popular products. Right? It has nothing, or it doesn't only have something to do with age, it also has something to do with other things. You can go higher than 2 variables, but then you go into crazy 3D plots, not really interpretable anymore, so that's a bit harder to visualize. So can we get the effect of knowing those interactions, but put it still on a 1-by-1 feature plot to split it out a little bit better? And indeed we can. That's the individual conditional expectation plot. So very similar to partial dependence plots, option 2. So again, for every instance that I have in my original data set, I'm going to keep you as you are, but I'm going to say, well, what if you're 21 years old? What if you're 28 years old? What if you're 32 years old? What if you're 42 years old? So similar to option 2 in my partial dependence plot. But now for every block of instances that share the same age, right, here they're spread out a little bit differently, but 21, 21, 21, 21, I will not simply average that prediction to a single line, but I will say, well, why not, if I do have those different predictions for the same original instance as I go over age, plot a line per instance that I have instead. So for the individual expectations for every instance separately. So now I take all of you and I change your ages or your RM, whatever this is, and I see how the model reacts. A bit more nasty to read correctly, so typically what we do is we also still plot an average line, the yellow one, and we make sure that they start from 0 to kind of see the increase in effect a little bit easier, so that we kind of put it to the 0 points relatively speaking. So now we still have that average partial dependence, which now can be flat, but now it can be flat because we see, yeah, but wait a second, like I'm going to draw the extreme case again, partial dependence, everything averaged together is flat, but if I look at all of those instances separately, I have like a whole group of them for which if age goes up, that they behave like this, and then there are other instances that behave like this. Yeah, if you average that down, flat, obviously, right? But what then this tells me is, yeah, but yeah, probably age is driving the outcome heavily, but I do also need to know another thing. Like, for instance, whether, I don't know what these two groups could be, right? That's whether you're a senior employee or you're a junior employee, for instance, or whatever, right? Or you work in engineering or you work in economics, right? So now this is easier to spot, and that's what these black lines show you. It says, okay, generally speaking, most of them do follow this general pattern. Like if age goes up, yeah, the prediction goes a bit lower, but for some of them, the prediction goes way lower than for others, right? So the effect is still a bit spread out, so probably we also need to bring in a second feature to explain this, or at least you see the variety across the predictions. So that's a very commonly utilized one still today, to look at it that way. Lime, now we focus our attention to specific instances. So, okay, that's all good. We know which features and how, but I do now have a particular instance, and your model told me, I'm pretty convinced that this is a positive case and I don't agree, right? Or I want to know why. And we can ask it in different ways. One way how we could ask it is, okay, what were the most contributing factors that caused your model to come to this prediction of 80% positive? What I could also do, and this is what Lime tries to do, in fact, is more in the terms of give me some sort of counterfactual style explanation, in the sense of what is the minimum or the minimal change that I can make to this instance to have your model change its mind. And then that will also probably tell me something about the things that were important, right? So that's Lime. Works with tabular, but also with other style of models. And how does it work? Okay, say we have a very complicated black box classifier. We don't know how it works. It's non-linear, and we want to explain a certain instance that we have. And my classifier tells me, well, 78% probability that it's a positive. What will I do? This is my data set. This is the instance that I want to predict, for instance, here. And this is the decision boundary of my complicated model, which is easy to see because we only have two features, x1 and x2, right? But pretend we have 100, and that is a 100-dimensional cube that we are playing in, and that this decision boundary, it's obviously not linear, it's all over the place, right? But there is some instance there, and it got a certain prediction from my original model. It's close to the decision boundary, but I'm convinced that it should be on the other side, right? So what could I change? What we do is we first create a synthetic bunch of instances by perturbing in my original feature space. And in the case of tabular data, what I can do here, for instance, is just between minus x2 and max x2 and min x1 and max x1, just pick instances that you create. But yeah, I'm mainly interested in the space around this instance. If you're all the way over there, I actually don't care, because what I will try to do is I will try to locally approximate the decision boundary of my complicated classifier, but only locally, because I don't want to go too far away from this particular instance. And because I'm only staying locally, I can probably get away with there trying to fit a linear separation boundary or decision boundary. So I'm going to weigh my instances. Basically, the closer you are to the original instance, the higher the weight that you get. Okay, next step is you take a sample again, like to reduce that synthetic set. And of course, you sample based on the weighing that you gave, so that closer samples have a higher chance to be picked. But okay, you just make sure that your synthetic set is in some way reasonably limited in size, let's say, and also close to the original instance that you had. And then you ask your original black box model, for all of these synthetic guys that I have created, please predict. These are continuous values, probabilities between 0 and 1. And then I want to estimate or approximate the decision boundary that is present locally around this instance. Now you can see locally it looks like a vertical line, right? And already here, based on the colors, you see that that same vertical line shows up. But I want to have an exact formulaic description of this vertical line. Well, we have a way to do that, obviously. What I do next is I take the features of these synthetic cases, x1 and x2. As my target, I use the predicted probability of the black box model that I already have, and I just stick it into a linear regression, right? Which is linear, which is what I want. And even more so, I'm going to heavily force this thing to not use all the 100 features that I have, or 2 in this case, but to throw away ones that it doesn't need. How do I do so? L1 regularization. Lasso. I will heavily regularize this thing. And then you see that the decision boundary that you get there, well, maps the decision boundary of my black box classifier, at least locally for this instance. And then I can inspect this lasso model that I've built there, and I can start to hunt for an explanation in terms of, well, now based on this simple model, what is the variable that I can play with to bring you from a yellow case to a purple case? Now, typically, multiple such explanations are possible. So you can either say, I'm looking for the explanation which is shortest in terms of coefficients that I need to change or variables that I need to adjust, or I want to look for an explanation which is smallest in terms of changes that I want to make. Right? You can play a bit with that, but there might be multiple explanations. Here, not, because I only have 2 variables and one doesn't matter. So you basically see, well, if you move this guy a little bit to the right, well, he would have shifted. Right? So it's this feature that caused you to make this decision there. That's how Lime works. If you want to try this out on other things, such as images, the thing that they change is to change the way how these synthetic instances are created. For instance, in the case of images, my original model says, well, I see a couple of things here. I see an electric guitar, but the probabilities for acoustic guitar are also high, and the probabilities for Labrador are also high. And I want to get some insight in terms of, well, how do you reach that conclusion now? So the same step as before. I have my original image, and let's say I'm trying to explain Labrador, right? And I don't agree, but I don't agree might also mean, well, what do I need to change for you to not see a Labrador anymore, to change your prediction? So I know, okay, the probability is, for instance, I'm picking out the one for Labrador, and it's pretty high, right, 0.8. So first I will create a whole set of perturbed versions for this instance. Well, what does that mean to perturb an image rather than features in a tabular data set? perturbing on the pixel level. Yeah, but then if I change individual pixels, there is possibly a lot of synthetic instances that I can create that way, and none of them are going to be very useful to show to a human. So instead, what I will first do, I will take my image that I have, and I will use k-means or some kind of clustering technique to say make 100 clusters of groups of pixels that are more or less the same in color anyway, and kind of divide the image first into groups like that. And then to create perturbed versions, you're going to generate new images where for some of the groups, you just keep them as they were originally, so you didn't change them. And for other groups, you hide them, you blank them out, meaning you replace them with their average value, which is gray in this case, right? So you basically hide them out. So then you create a whole bunch of images like this, right? And you also ask the model to make predictions. So for all of these images, it gives you a separate prediction. But then, how does the lasso step work? Well, actually, more or less in the same way, because now what we have done for all of our images that we have, these perturbed instances, we have utilized k-means here. So we have, let's say, 10 groups of superpixels. Cluster 1, cluster 2, cluster 3. And for every image, we know that we have kept some groups as they are, and we have grayed out some other groups. So our feature vector is this the original, like in the normal image, or is this the chain, or did we gray this cluster out? So now I can describe all of my images that I have perturbed as basically a 0, 1 feature vector. I know the prediction of my black box model, like probability of being a dog here is only 0.2. Here it stayed the same, 0.8. I again then train an L1 linear regression model on top of this, where I say, well, try to focus only on the groups that matter most, on the features that matter most. And from there, I might then explain or extract an explanation that says, well, you know, in this instance that you have there, the instance that you have means all of the clusters are shown, so are 0. But if you bring cluster 2 from 0 to 1, the probability already drops heavily. Oh, what is that cluster that brings me from probability 80% to 20%? Well, it's this cluster that you need to change, and it's this cluster that you need to change. Yeah, indeed, if I hide the doggy face, the model changes its mind. And that's how you do this on images. And also for text, if you can think up a way to perturb your instances, like replace text with synonyms or drop maybe fragments of text, you can set up something similar. Now, what we didn't really do is for these images, in the tabular step, we said, well, we also sample in such a way where you only keep the local neighborhood. Here for the images, we really didn't do that. We just perturbed them, and we kind of hoped that the fact that we clustered them together already gave us a good global neighborhood, or a good neighborhood around this local instance, right? Because for every perturbation that we do, well, we could perturb in such a way where we make everything gray. And probably for that one, we would say, well, remember here in feature space, my original image is all the clusters are shown. The heaviest perturbation is to hide all of these clusters. So I will probably not do that. Maybe I'm only going to hide away 3 clusters at most, right? Or I would sample based on this kind of distance between everything shown, everything hidden. You would have to come up with similar distances for other types of data as well. But it is kind of appealing, it is kind of elegant, it's a smart idea, it's creative, it's not hard, right? You could have come up with this yourself based on what you know already. So this was very commonly used for a while. Now less so, because there are some parameters that you can play a bit with, like how strong should the regularization be of that lasso model that you train? The stronger that you make it, the shorter your explanations will become, obviously, but maybe also the less well explained that things might get. And then the explanations themselves, should that be a long explanation that touches a lot of variables but only touches them a little bit, or should it only touch a couple of variables but touches them heavily? Very often you have more than one possible explanation to step over the decision boundary from one instance to the other outcome. Which one is then the best one? Hard to say. And it's also important to say that this is then an explanation, but not the only explanation, right? There might be other groups that we could have hidden here, which are also a very good explanation. So we only show typically one of them, not the whole set of possible explanations. So in that sense, they're maybe not the best explanations that we could get out. So for that reason, another approach, something called Shapley values, has taken over as being the most popular one up until today, at least for tabular data applications. And it stems from game theory, so originally it had nothing to do with machine learning, from Lord Shapley, who won the Nobel Prize for this. And in essence, it's a theoretical concept which is mainly concerned about things such as a fair assignment of payout to all of the players that are playing together in a cooperative game. So you have a game which you play as a team of people. At the end, you get a score for your team. But what I'm concerned about as the manager of my team is, okay, well done. You went out into the tall grass and you caught 20 Pokemon, right? But you were 5 of you in the team. How should I distribute that 20, that score, over each individual player? How well did each of you contribute, or how did each of you contribute to gain that total score? Perhaps there were some of you that did better than others, right? So how do I decide the one that will get a promotion, let's say? So we play a game. So let's say we have a team of 5 people, and I let you play, right? And you come back with a certain score. But what I could do is I could say, well, a way to set this up, and again, this is from the theoretical perspective where we could run some experiments, right? But I could say, well, player A, how about you go out alone and you play this game and then tell me what you get back? And you will not come back with the full, 20 Pokemon, or I don't know what the score is in the end, but at your own, cooperatively, you won't do so well. You will only come back with 6. And I would say, okay, good, 6. And then I say, okay, tomorrow, both player A and B go out together. And then you come back with 10. I say, but player A on their own, they could already give me 6, so B must mean that you are doing 4 better than A. So I'm going to give you a payout of 4, and A, I will give 6. And then the next day, I have A, B, C, I get 12, so I would say, well, C, your marginal contribution is 2, so you get 2, B gets 4, A gets 6. So far, so good, except that if you would be player C in this comparison, what would you tell me? Would you be happy that I give you 2? No, right? Because you would say, oh, you didn't give me a fair chance, right? And why didn't I give you a fair chance? You should also have allowed me to go out on my own, right? Who knows what I could have gotten on my own, right? This order that you established to start with A first and then B and then me is not really fair. I will say, yeah, you're right. So what I should do instead, I should take all of these marginal contributions, but I should average them over all possible orderings that I can construct. So not only do I need to know, dear C, what value did you add to A and B, but I also need to check if I would have started with A and D and then added you. I also need to see what your value is. And if I start with an empty team and I add you, I also need to see what your value is. And only by averaging all of those differences in ways how I could have added you, that will add up to a fair average payout for you. But what I do know is, at least you will agree, that I can expect that if I start today and I first have added A and then B to the team, and then the next day I add you, or the 2 days before I first started with B and then A, and then I added you, that your marginal contribution is going to be the same in both cases. So the order of my previous choices doesn't matter. And what I also know is what I will do afterwards, after adding you in the next step, that for you, in this situation, that also doesn't matter. Right? So what I will do tomorrow for D and so on, that doesn't influence my contribution for C. So what I can do is I can exact average all of this, or I can average all of this together. So I say, okay, the value of a player J in this total group of players that I have, I need to know their contribution to every possible sub-team that I can form. So the sum over all the unordered subsets that I can make with the other players. So all the subsets that I can make with all the other players except you, right? And then given all the permutations of players in that team that I have formed, because I want to shuffle over all the possible orderings that might have been so far, times all the possible ways how I can make the rest of the group, right? Possible number of teams. And then just, okay, what is then the value that you added to that team minus the value that the team without you did in that particular configuration, and average all of that together. And the average all of that together, that's this denormalization factor, the total number of possible combinations that I'm checking here, basically. And then that's your Shapley value in this game. Aha! What are my players in a machine learning model? Given the prediction of a particular black box model for a particular instance. That's the game that's being played. The game is you're making a prediction. The value of the team as a whole is the prediction that I got from my model, a probability or a regression outcome, something like that. Okay, so to play that particular instance, to get that particular prediction, who are the players? The players are my features with that particular value that they have for the particular instance that I'm playing on. Right? So not just the features, but specifically for this instance. Right? So I will calculate the Shapley values per feature per instance. They might be different for the features as I'm looking over different instances, because the values will be different. So here it's not just that the features, or like you have 10 features and so there are 10 players, and no, it's really like the features with their value that they have. But okay, for one particular instance, it's the features. So what I would like to do is I could test out, okay, now we know how this works. Start with a model that has no features. What is the prediction that it would make? And then I'm going to add in feature A. And I'm also going to add in feature B. And I will try every possible ordering of this. And then I will average all over that. And this will give me the Shapley value per feature for this particular instance's prediction. But I can't just drop out features from my model and play the game again. That works with my Pokemon, where I can keep some players home. But here, that would mean that I would need all these retrained versions of my model, and also retrain in a way where the ordering of bringing in the features matters. So that wouldn't really work. So we come up with a way to simulate it by means of Monte Carlo sampling, which is again based on permutation, if you will, but which simulates the exact same kind of all the different orderings and averaging those together. So again, here we're going to set up a simulation. We're going to say, well, we can estimate the value for each player, right? And the way how we estimate it is we run over many rounds, and we average over many rounds, and we're also going to subtract the value of you minus the value of something without you, right? In this case, we're going to subtract the prediction of my model for two types of instances. One instance, which I call subscript plus j, and one instance, which I call subscript minus j. Here we did the exact same thing, but here we said, well, what would the prediction be of this model with your feature included, minus the prediction of a model that doesn't use your feature? But we don't want to do that, so we use this instead. What are these instances plus j and minus j? Well, as follows. What we do is we pick a random, so we already have the instance for which we are trying to get our Shapley values for. So that's chosen, that's x. So we have a certain instance with which features, and we want to know the contribution of every player. What we do is, for every of these rounds, we pick another random instance, which we call z, from our data. And then we're going to permute again a little bit. So my instance x, in each of my rounds, that stays the same. But for every iteration here, I pick a z. And then I say, well, what I will do is I will pick, and here the way how it's visualized, what I will pick is I'm looking at my player j, that's the one that I want to calculate my contribution for. So that one is also fixed. And here in this case, j is equal to f, variable f. That's the one I would like to know what is your Shapley value. So that one I don't touch, right? These I keep the same, so x stays 2 and z stays 4, right? And those two become my plus j and minus j. So plus j basically means what is the original value that you saw in x for f, minus j was the one that you took from a random instance. What do I do with the other features? Well, I make two groups out of them, and I say, well, just distribute them randomly over either shift them to be equal to x or shift them to be equal to z. So there basically what you do is for every feature you randomly pick, either set both equal to what x was or set both equal to what z was. So you also get a permutation effect where you try to wash out, you try to average out only the contribution of the x or the j feature, the f in this case, versus the others. And if you do this enough times, tens of thousands of times, the Shapley value that you will get here will be the same as the one that the theoretical one gives you. And now what you will have is for every feature for an instance x, it will tell you what was the Shapley value for that feature to reach your model's predicted value for x. For instance, if my features are BMI equals 40, BP, blood pressure equals 180, sex equals female, age equals 65, my model predicts 40% likely to, what this is, catch cancer, or I don't know what this is, right? The values that you see here, this plus 0.4 and this minus 0.3, those are the Shapley values of my 4 features for this instance. Meaning that if I know that the average prediction of my model is 0.1, that's where everything starts from, right? Here is how the features contributed to construct a final prediction, and nicely enough here, in an additive way. So knowing that BMI equals 40, push the prediction up by 0.1 probability. Knowing that the blood pressure is 180, also pushed it to the right. The fact that you're female, that's good news. Pushes it to the left again with 0.3. But then your age, 0.4 back to the right. And you end up with a final predicted output of 0.4. What is the nice thing here now is that if I would ask you which features had a downwards effect versus an upwards effect, you can clearly see that. If I ask you which features, at least for this instance, which feature was the most important one, the one with the highest contributing factor. And now what will happen if not only I get these Shapley values for just one instance, but for all of the instances that I have, they will be different for all of these features, is that I can start to plot them in a plot like this. So this is the same thing, explaining a single instance. So the length of the arrow gives me the Shapley value. The higher the length, the more important the feature is. Upwards effect, downwards effect. But then if I do this for all of these instances, I can make a summary plot like this. The value on the x-axis, so now let's take a look at one of the features that you see in here, age, for instance. For this single feature, I get multiple dots. Why? Because I'm calculating the Shapley value for age for every instance that I have. Right? The size that I see on the x-axis gives me the contribution that the feature age had for each of these dots. In some cases, a negative contribution. It pushed the prediction downwards. For some of the cases, an upwards contribution. For some cases, not a contribution at all. Because maybe, well, age often matters, but sometimes doesn't matter. Again, it has to do with interaction effects, right? The color of the dot shows me what the actual value of the feature was for that instance, right? So to see, well, maybe higher values for age have stronger positive Shapley values. What I can then do is I can use the spread of the Shapley value, lowest to highest value, to get like an overall importance ranking. So here I see that the number that you have taken hormonal contraceptives in years is an important or is the most important feature. As I go to the right and I start to inspect instances where indeed the contribution is very high in terms of you getting cancer, right? Is this then when your years of taking hormonal contraceptives are high or low? Well, they're red dots. So high. So the higher the number of years, Not for everybody, right? There are cases with a high red value here that show even up over here, right? But in terms of overall impact, this is the most important one. If you smoke, kind of similar effect, right? If you have an IUD and so on. You can even then say, plot 2 of these features so that you can start spotting the interaction effect. So here is hormonal contraceptive years again. This is the value of the feature now in the x-axis. And here at the y-axis, the Shapley value again. So we've taken the x-axis over here and we've thrown that on the left. And we indeed see that for, these red cases over here, we do find cases where as we use, or as we have a whole number of years, 30 years, 25 years of usage, then indeed for some of them, the Shapley value is very high. But I also told you there are cases which are pretty high, like this one, for instance, or cases which have a lot of years, like this one, let's say, where the Shapley value is not that high yet, right? Still okay. You have taken it for a lot of years, but the impact is not so high. So maybe there is an interaction effect present. We can even hunt for that automatically. So here is the technique itself suggests, well, if you also overlay a second feature, which luckily is a binary one, so only 2 possible colors, green or blue, namely the fact whether you have had an STD or not, this helps to further explain the behavior in terms of Shapley value of hormonal contraceptive years, right? Because now you see that kind of the effect in terms of things going up, right, differs in terms of whether you've had an STD or not. And weirdly enough, here in this case, for the green cases, so if there is an STD, the overall impact in terms of Shapley value, in terms of taking contraceptives, as you do that for a longer amount of years, seems to be lower actually than if you haven't. Now you can then play in and look with interaction, or you can just zoom in, like this case, on one single instance and fully explain it. It's not easy to fully understand that, like you can show this plot to a stakeholder and expect, well, you see, age is most important, so you do need to explain a bit. There is a difference between feature value and Shapley value here, right? But you can basically get all of the things that we did so far, partial dependence, interaction effects, instance level explanations, and an overall importance ranking, out of the same technique. And we will see that you can also utilize this on images, and you can utilize this is model agnostic, right? Because it takes the model as a black box. So hence why this one, especially for tabular approaches, is still the most popular one today. Now, there are some further readings that you can check out, not obligated to do so. The most important one here is the free book Interpretable Machine Learning. If you'll be interested in knowing a couple more tools that you can utilize, fantastic resource. It goes in a couple of extra interpretability techniques as well, such as counterfactuals and so on, and rule-based techniques. So do check that out. Good, I think that's enough for today. I will see you next week.